Hey there, and welcome to the Night Scientist of the Universe. I'm so happy you're here with me today. There's something truly magical about taking a moment to slow down, to breathe deeply, and to explore the incredible stories that our cosmos has to tell. Whether you're curled up in your favourite chair, taking a gentle walk, or simply finding a quiet moment in your day, I want you to know that this is your time to relax and wonder. You know, there's something profoundly comforting about understanding our place in this vast, beautiful universe. Every story we explore together is really a story about us, about our home, about the incredible journey that brought us to this very moment. And today, we're going to embark on one of the most remarkable tales ever told, a story that spans billions of years, involves cosmic collisions, stellar nurseries, and the gentle dance of chemistry that made life itself possible. Today we are diving into the fascinating world of how Earth learned to hold liquid water. It's a story that begins in the violent birth of our planet, travels through epochs of fire and ice, and ultimately reveals how our blue marble became the perfect cradle for life. This isn't just a tale of physics and chemistry, it's a love story between a planet and the precious substance that makes all life possible. So settle in, let your mind wander, and let's explore together how our Earth became the water world we call home. Imagine, if you will, drifting through space and time back to a moment roughly 4.5 billion years ago. The universe around you is younger, wilder, more chaotic than the gentle cosmos we know today. In this ancient realm, our solar system is nothing more than a swirling disk of dust and gas, a cosmic nursery where planets are about to be born through processes so violent they would make the most dramatic earthly storm seem like gentle summer rain. In the heart of this spinning disk, our young sun has just ignited, beginning its long journey as a stable star. But around it, the space that will one day hold our familiar planets is filled with countless pieces of debris, from tiny grains of cosmic dust no bigger than the period at the end of this sentence, to massive chunks of rock and ice the size of mountains. These building blocks are dancing a gravitational ballet, slowly but inevitably coming together through a process that scientists call accretion. Picture these early moments like a cosmic snowball fight. Except instead of soft snow, imagine chunks of rock, metal, and ice hurling through space at speeds that would make our fastest rockets seem like they're standing still. As these pieces collide and stick together, they form larger and larger bodies. What starts as dust becomes pebbles. Pebbles become boulders, boulders become mountains, and mountains become the embryonic planets we call planetesimals. Our Earth begins its life as one of these growing planetesimals, somewhere in what scientists call the habitable zone, that perfect distance from the sun where temperatures are just right for liquid water to exist. But don't mistake this early Earth for the peaceful blue marble we know and love. This infant planet is a world of unimaginable violence, a hellish sphere where the very air would burn your lungs and the ground beneath your feet would melt your shoes in seconds. The process of planetary formation is like a cosmic construction project that never stops, never sleeps, and never slows down. Every few minutes, sometimes every few seconds, massive objects slam into our growing Earth with the force of billions of atomic bombs. Each impact releases enormous amounts of energy, heating the planet's surface to temperatures that would make molten lava seem cool by comparison. The entire surface is an ocean of liquid rock, a magma sea that glows red-hot against the black of space. During these early eons, which scientists poetically call the Hadean era, named after Hades, the ancient realm of fire and brimstone, our planet resembles nothing so much as a ball of molten metal and rock spinning through space. The atmosphere, if you can call it that, is a toxic soup of hydrogen, helium, water vapor, carbon dioxide, and other gases that would be instantly lethal to any form of life we know. Lightning crackles constantly through these thick, choking clouds, and the very ground pulses with heat like a planetary heartbeat. But here's where the story becomes truly remarkable. Even in this apparent chaos, the seeds of something beautiful are being planted. You see, many of those asteroid and comet impacts that are turning our planet into a hellish furnace are also delivering something precious. Water. Not liquid water, of course, because the surface temperatures would instantly vaporize any liquid, but water molecules locked in ice within comets, and water bound up in the crystal structures of certain types of rocks called hydrated minerals. Think of these early impacts like cosmic deliveries, each one bringing a little more of the ingredients that will eventually make our planet a haven for life. The comets, those beautiful dirty snowballs from the outer reaches of our solar system, are particularly important in this story. They form in the cold, distant regions beyond Neptune, where temperatures are so low that water, carbon dioxide, methane, and other compounds can freeze solid and stick together with dust and rocky debris. When these ancient comets come careening toward the inner solar system, drawn by the gravitational pull of the Sun and the growing planets, they carry with them the frozen remnants of the original solar nebula, the cloud of gas and dust from which our entire solar system formed. It's like they're bringing messages from the very beginning of our cosmic story, delivering the essential ingredients for life from the outer darkness into the warm embrace of the inner solar system. As each comet strikes the molten surface of the early Earth, it releases its cargo of ice, which instantly vaporizes in the intense heat and joins the thick, steam-laden atmosphere surrounding our planet. This water vapor doesn't just disappear, it accumulates, building up in the atmosphere like a vast planetary-scale pressure cooker. The early Earth is literally surrounded by a thick blanket of superheated steam, held in place by the planet's growing gravitational field. But the story of Earth's water doesn't begin and end with comets. The rocky asteroids that slam into our planet during this violent period also contribute to our growing water reserves. Many of these asteroids formed in regions of the early solar system, where they could incorporate water molecules into their very structure. When these water-bearing rocks impact the Earth, they release their hidden moisture, adding yet more steam to our planet's increasingly thick and humid atmosphere. During these early times, the line between solid ground and atmosphere is blurred beyond recognition. The surface of the Earth is covered by what scientists call a magma ocean, a layer of molten rock that might be hundreds of miles deep. This liquid rock sea is constantly churning, mixing, and being renewed by the endless bombardment from space. Any water that manages to condense and fall as rain immediately boils away again, creating a cycle of evaporation and precipitation that exists entirely in vapor form. As we continue our journey through Earth's violent infancy, let's pause for a moment to truly appreciate the scale of chaos that surrounded our planet during those early epochs. If you could somehow travel back in time and observe the Earth from a safe distance, though nowhere in the early solar system would truly be safe, you would see a world that defies everything we think we know about planets. The young Earth spins much faster than it does today, completing a full rotation in just 6 hours instead of our familiar 24. This rapid spinning creates fierce winds in the thick atmosphere, winds that would make the strongest hurricanes on modern Earth seem like gentle breezes. The entire planet is wrapped in clouds so thick and dense that no sunlight penetrates to the surface. From space, Earth would appear as a featureless reddish-brown ball, glowing with its own internal heat like a small star. But the most dramatic feature of this ancient world isn't visible from space. It's the constant, relentless bombardment that continues to shape and reshape the planet's surface. Scientists call this period the Late Heavy Bombardment, and it represents one of the most violent chapters in our planet's entire history. Imagine living through a time when the sky literally falls on a regular basis, when mountain-sized objects slam into the Earth with such force that they can be seen and felt from thousands of miles away. Each major impact during this period releases energy equivalent to millions of the most powerful volcanic eruptions happening all at once. The shock waves from these collisions travel through the solid rock of the planet like ripples through water, causing earthquakes that would dwarf anything recorded in human history. Mountains rise and fall in a matter of hours, continents are born and destroyed, and the very shape of the planet changes with each major collision. Yet even in this seemingly hostile environment, the processes that will eventually make Earth habitable are already beginning to work their subtle magic. The massive energy released by these impacts doesn't just destroy, it also creates. The heat from collisions helps to drive chemical reactions that wouldn't be possible under cooler conditions. Elements that were once locked away in solid rock are free to move and combine in new ways, setting the stage for the complex chemistry that life will eventually require. During this chaotic period, something truly remarkable happens, an event so dramatic that it will shape the character of our planet for the rest of its existence. A Mars-sized object, which scientists have nicknamed Thea, after the Greek goddess, comes barreling toward Earth on a collision course that will change everything. This isn't just another impact in the endless bombardment, This is a collision of such magnitude that it will literally reshape both objects involved. When Theia strikes the Earth, the collision is so violent that it vaporizes both the impactor and a significant portion of our planet's outer layers. Imagine trying to visualize an explosion so powerful that it launches molten rock and vaporized metal all the way into space, creating a ring of debris around the Earth like the rings of Saturn, but made of liquid rock instead of ice. This debris ring will eventually cool and condense to form our moon, the cosmic companion that will play such a crucial role in making Earth suitable for life. But this giant impact does more than just create the moon. It also has profound effects on Earth's ability to hold onto water. The collision gives our planet a significant tilt, about 23.5 degrees, which creates the seasons that help moderate our climate. It also helps to stabilize Earth's rotation, preventing the wild wobbling that would make our planet's climate chaotic and unpredictable. Perhaps most importantly, the energy from this massive impact helps to drive the formation of Earth's iron core, which will eventually generate the magnetic field that protects our atmosphere from being stripped away by the solar wind. As the debris from the giant impact settles and the moon begins to take shape in orbit around Earth, our planet starts to show the first signs of the stability that will eventually allow liquid water to exist on its surface. But we're still a long way from the peaceful blue world we know today. The surface remains a hellish landscape of molten rock, the atmosphere is still thick with steam and toxic gases, and the bombardment from space continues, though with somewhat less intensity than before. During this period, the water that has been accumulating in Earth's atmosphere as steam begins to play an increasingly important role in shaping the planet's evolution. This water vapor acts like a greenhouse gas, trapping heat from the sun and from the planet's own internal warmth. But it also helps to moderate temperature extremes, preventing the surface from becoming either too hot or too cold for the complex chemistry that will eventually give rise to life. The thick atmosphere of steam also helps to protect the surface from some of the smaller impacts that continue to pepper the planet. When meteorites and asteroids encounter this dense, humid atmosphere, they burn up more completely than they would in a thinner atmosphere, reducing the number of objects that actually reach the ground. It's as if the Earth is gradually learning to protect itself, developing its own natural defenses against the hostile environment of the early solar system. As millions of years pass, the frequency of major impacts begins to decrease. The solar system is slowly cleaning itself up, with the largest objects either having already collided with planets or been ejected into the outer darkness. The surface of the Earth, while still hot and unstable, begins to show signs of cooling. The magma ocean that has covered the planet for so long starts to develop a thin, unstable crust in some areas, islands of solid rock floating on an ocean of molten stone. This crustal formation marks a crucial turning point in Earth's ability to hold liquid water. For the first time since the planet's formation, there are stable surfaces that might be cool enough for water to exist in liquid form, at least temporarily. Of course, these early crustal patches are constantly being destroyed and reformed by volcanic activity and the ongoing bombardment from space, but they represent the first tentative steps toward the solid, stable surface that liquid water requires. Now comes one of the most beautiful and transformative moments in our planet's entire history, a moment that deserves to be told with all the wonder and reverence it deserves. After hundreds of millions of years of violence and chaos, after countless impacts and endless volcanic eruptions, something magical is about to happen. The Earth is finally cool enough, stable enough, and ready enough to experience its first rainfall. But this isn't going to be a gentle spring shower, or even a dramatic thunderstorm. This is going to be rain on a scale that defies human comprehension, a downpour that will last not for hours or days, but for millions of years. Scientists sometimes call this period the Great Rain, and it represents one of the most important transitions in our planet's entire history. This is the moment when Earth finally learns to hold liquid water. Picture the scene. The surface temperature has finally dropped below the boiling point of water, at least in some regions and at certain times. The thick, steam-laden atmosphere that has surrounded our planet for so long is finally cool enough for water vapor to condense into liquid droplets. For the first time in Earth's history, clouds begin to form, not the thin, wispy clouds we see today, but massive, towering formations that stretch from the surface all the way to the edge of space. These early clouds are unlike anything we've ever seen. They're thick with water vapor that has been accumulating in the atmosphere for hundreds of millions of years. When the first raindrops begin to fall, they're not the small, gentle drops we're familiar with, but massive globules of water that strike the hot surface with tremendous force. The sound would be deafening, like a trillion drums beating all at once across the entire planet. When these first raindrops hit the still hot surface, many of them instantly vaporize again, creating clouds of steam that rise back into the atmosphere. It's a delicate dance between cooling and heating, between liquid and vapor, between the sky and the ground. Some areas of the surface are still too hot for liquid water to survive, while others are just cool enough for puddles to form, however briefly. But as the centuries pass, more and more of the surface cools to the point where rainwater can survive contact with the ground. These first permanent pools of liquid water are small and temporary, constantly evaporating and being replenished by new rainfall. They form in the lowest areas of the landscape, in valleys and depressions created by ancient impacts or volcanic activity. The chemical composition of this early rainwater is nothing like the pure water we think of today. It's acidic from dissolved atmospheric gases, rich in dissolved minerals from its journey through the thick atmosphere, and probably tinged with a rainbow of colours from the various compounds it has picked up along the way. This water is chemically active, eagerly reacting with the rocks and minerals it encounters on the surface. As this mineral-rich water flows across the landscape, it begins to carve the first river channels in Earth's crust. These early rivers are unlike anything we see today. They flow across a landscape still dominated by volcanic activity, still marked by the scars of ancient impacts. The water hisses and steams as it flows over hot rocks, creating a landscape of geysers, hot springs, and thermal pools that would make Yellowstone National Park seem tame by comparison. But perhaps the most remarkable thing about these early rivers is where they're heading. They flow downhill, as all rivers do, seeking the lowest points in the landscape. And as they converge and combine, they begin to create something that has never existed before on Earth. Large bodies of standing water. The very first lakes are being born. These early lakes are small by modern standards, and they're constantly changing as the landscape around them shifts and evolves. Volcanic eruptions can drain them overnight, or create new ones in a matter of hours, but they represent something profoundly important. They're the first stable reservoirs of liquid water on our planet's surface. As the Great Rain continues, century after century, millennium after millennium, these lakes grow larger and more stable. The continued cooling of the planet's surface means that more and more areas become suitable for liquid water. The rain becomes less intense but more persistent, creating a more stable water cycle than the violent evaporation and condensation that characterized the early period. During this time, something truly remarkable begins to happen in the chemistry of these early water bodies. The mineral-rich water becomes a kind of natural laboratory where complex chemical reactions can take place. Elements that have never had the chance to interact begin to combine in new ways. Carbon, hydrogen, oxygen, nitrogen, sulfur, and phosphorus, the building blocks of life, begin to form increasingly complex molecules in the warm, nutrient-rich waters.
The first organic compounds are being synthesized in these ancient lakes and pools. Simple molecules like amino acids and nucleotides, the building blocks of proteins and DNA, begin to appear in the chemical soup that fills these early water bodies. It's still billions of years before anything we would recognize as life will emerge. But the stage is being set for one of the most remarkable transformations in the universe. As the Great Rain continues, the individual lakes and rivers begin to connect with each other. Small streams merge into larger rivers, lakes overflow their banks and create new waterways, and gradually, a network of connected water bodies begins to span the planet. For the first time in Earth's history, water can flow from one side of the planet to the other, carrying dissolved minerals, organic compounds, and energy along with it. This global water cycle also begins to have profound effects on the planet's climate. The evaporation of water from lakes and rivers creates clouds that help regulate temperature, preventing extreme heat during the day and extreme cold at night. The water cycle becomes a kind of planetary thermostat, helping to maintain conditions that are favorable for liquid water to persist, but the most dramatic change is yet to come. As the centuries pass and the rain continues to fall, the individual. Lakes and river systems begin to merge into something much larger. The lowest areas of the planet's surface, vast basins created by ancient impacts and tectonic activity, begin to fill with water. The first seas are being born. These early seas are nothing like the vast oceans we know today. They're shallow, mineral-rich, and constantly changing as the young planet's surface continues to evolve. But they represent a quantum leap in Earth's ability to store and cycle water. For the first time, truly massive amounts of liquid water exist in stable reservoirs on the planet's surface. The formation of these early seas marks the end of one chapter in Earth's story and the beginning of another. The violent, chaotic period of planetary formation is finally giving way to something more stable and predictable. The stage is being set for the next phase of our planet's evolution, the emergence of the global ocean system that will make complex life possible in the grand theater of space. 4.5 billion years ago, our young Earth found itself at the center of what we might call the universe's most spectacular delivery service. Picture, if you will, a cosmic post office where packages aren't wrapped in brown paper and string, but instead are gleaming chunks of ice and rock hurtling through the darkness at speeds that would make your head spin. These weren't ordinary deliveries, mind you. These were special deliveries that would change the very nature of our planet forever. The Earth of this time was nothing like the blue marble we know and love today. It was a world caught between fire and ice, a place where the very ground beneath what would one day become your feet was still learning how to be solid. The surface temperature fluctuated wildly, sometimes hot enough to melt lead, other times cold enough to freeze the very air itself. And yet, in this seemingly impossible environment, something magical was beginning to happen. The universe was about to teach Earth one of its most important lessons: how to hold onto water. To understand this cosmic lesson, we need to travel back in time and witness what scientists call the late heavy bombardment, though I prefer to think of it as the Great Water Delivery. Imagine you're floating in space, watching our solar system like a snow globe that someone has just shaken vigorously. Everywhere you look, there are objects in motion, comets with their magnificent tails streaming behind them, like cosmic wedding trains, asteroids tumbling end over end in their ancient dance, and countless smaller pieces of debris, each one carrying its own precious cargo of frozen water. The story begins in the outer reaches of our solar system, in regions so cold and distant that water doesn't exist as a liquid or even as vapor, but only as ice harder than granite. Here, in the realm beyond Neptune, in a place we call the Kuiper Belt, and even further out in the mysterious Oort cloud, billions upon billions of icy bodies waited patiently in the cosmic cold. These weren't just random chunks of ice, though. They were libraries of frozen history, each one containing within its crystalline structure the story of the early solar system's formation. Think of these icy visitors as cosmic time capsules. When you hold an ice cube from your freezer, you're holding water that was liquid just hours ago. But these cosmic ice cubes held water that had been frozen for millions of years, preserving within their cores the chemical signatures of the primordial cloud from which our entire solar system was born. Some of these frozen messengers carried not just water, but also organic compounds, the basic building blocks of life itself. In a very real sense, they were carrying the future in their icy embrace. The journey of these water-bearers from the outer solar system to Earth wasn't a smooth, planned voyage. It was more like a cosmic pinball game, where gravitational interactions between the giant planets Jupiter, Saturn, Uranus, and Neptune would occasionally nudge these icy bodies out of their comfortable orbits and send them careening toward the inner solar system. Jupiter, in particular, played the role of both protector and disturber. Its massive gravitational field would sometimes act like a cosmic slingshot, flinging comets and asteroids inward toward the realm of the rocky planets. As these icy visitors approached the inner solar system, they began to change. The gentle warmth of our sun, still so far away but so much warmer than the frigid depths they had known, began to work its magic on their frozen surfaces. Like flowers slowly opening to the morning sun, these cosmic ice balls began to develop their characteristic tails. Not one tail, but often two. One tail was made of dust particles liberated from the ice as it sublimated directly from solid to gas, creating a curved golden trail that followed the comet's orbital path. The other tail, straighter and often blue-white in color, was made of ionized gas, water vapor, and other compounds that had been electrified by the solar wind and were streaming away from the sun in a magnificent cosmic display. But it wasn't just the spectacular comets that were delivering water to our young Earth. The asteroid belt, that collection of rocky debris between Mars and Jupiter, held its own secrets. Many of these asteroids, particularly those in the outer regions of the belt, contained significant amounts of water locked within their mineral structures. These weren't the dramatic, tail-streaming visitors that comets were, but they were no less important. They were like steady, reliable delivery trucks, carrying their precious cargo of hydrated minerals. On collision courses with the inner planets, when these cosmic water-bearers finally reached Earth, their arrival was anything but gentle. Imagine the most spectacular fireworks display you've ever seen. Then multiply that by 1,000,000 and stretch it out over hundreds of millions of years. Each impact was a colossal event that would have dwarfed any natural disaster in recorded human history. The larger impacts would have created explosion craters hundreds of miles across, throwing molten rock and vaporized water high into the atmosphere, where it would eventually cool and rain back down onto the surface. The process wasn't always efficient, though. Many of these water deliveries came at speeds so tremendous, often tens of thousands of miles per hour, that the impact energy was enough to vaporize not just the incoming water, but also any water that might have already been present on Earth's surface. It was like trying to fill a bathtub while someone was simultaneously taking a blowtorch to it. For every drop of water successfully delivered, several more were blasted back into space as superheated steam. But Earth was patient, and the universe was persistent. For every impact that destroyed water, there were others that delivered it under just the right conditions. Some of the smaller impacts, particularly those that occurred as Earth's surface began to cool and stabilize, were gentle enough, if we can call multi-megaton explosions gentle, to deliver their water without completely vaporizing it. These successful deliveries began to accumulate, creating the first tentative pools and lakes on our planet's surface. The water that arrived during this cosmic bombardment wasn't all the same either. It came from different sources and carried different chemical signatures, like cosmic fingerprints that scientists can still read today. Water from comets originating in the Kuiper Belt had one isotopic signature, while water from asteroids in the outer belt had another. Water from comets born in the even more distant Oort cloud carried yet another unique signature. By studying the ratios of different isotopes of hydrogen and oxygen in Earth's current water supply, scientists can piece together this ancient story of cosmic delivery. One of the most fascinating discoveries in recent years has been the realization that much of Earth's water might not have come from the spectacular, long-period comets that we often see gracing our night skies today. Instead, a significant portion might have arrived courtesy of asteroids and short-period comets from the asteroid belt and Kuiper belt. These less dramatic messengers carried water that more closely matches the isotopic signature of water in our oceans today. It's a humbling reminder that sometimes the most important deliveries come not with fanfare and spectacular displays, but quietly and steadily over long periods of time. As Earth continued to receive its cosmic water deliveries, a new challenge emerged, one that would determine whether our planet would become the water world we know today, or remain a dry, barren rock like so many others scattered throughout the universe. The challenge wasn't just about receiving water, it was about learning to hold on to it. And this lesson would prove to be one of the most difficult and crucial in Earth's entire education. Picture our planet during this tumultuous period as a student trying to catch raindrops in a bucket while standing in a hurricane. The cosmic bombardment was delivering water, yes, but the same violent processes that brought water to Earth were also creating conditions that could easily strip it away. The young Earth was like a cosmic balancing act, teetering between becoming a water world and losing its precious gift back to the void of space. The key to this cosmic balancing act lay in a delicate interplay of factors that had to align just right. First, there was the matter of Earth's size and mass. Our planet needed to be large enough to generate sufficient gravitational pull to hold onto water vapor in its atmosphere, but not so large that it would become a gas giant like Jupiter, with an atmosphere so thick and crushing that liquid water could never exist on its surface. Earth hit this Goldilocks zone perfectly, not too big, not too small, but just right. But size alone wasn't enough. Earth also needed to be at just the right distance from the sun, close enough that water wouldn't freeze solid permanently, but far enough away that it wouldn't immediately boil away into space. This orbital sweet spot, which scientists call the habitable zone, is sometimes referred to as the Goldilocks zone, and Earth sits right in its midst like a cosmic fairy tale come to life. Even with the right size and the right distance from the sun, Earth faced another monumental challenge: its atmosphere. In those early days, our planet's atmosphere was nothing like the oxygen-rich envelope that sustains us today. Instead, it was a chaotic mixture of gases being constantly replenished by volcanic outgassing, modified by incoming cosmic debris, and stripped away by the solar wind. Learning to maintain a stable atmosphere that could hold water vapor was like trying to keep a soap bubble intact in a windstorm. The young sun, our cosmic neighbor and energy source, was both helper and hindrance. In this process, while it provided the warmth necessary to keep water liquid, it was also much more active and violent than the stable star we know today. Solar flares and coronal mass ejections, enormous eruptions of charged particles and magnetic energy, would regularly blast toward Earth with enough force to strip away portions of our atmosphere. Without some form of protection, these solar storms would have gradually eroded away any water vapor that Earth managed to accumulate. This is where one of Earth's most remarkable features began to play a crucial role: its magnetic field. Deep within our planet's core, something extraordinary was happening. The combination of Earth's rotation and the churning of liquid iron in its outer core was generating a magnetic dynamo, a planetary-scale electromagnetic field that extended far out into space. This magnetic field became Earth's invisible shield, deflecting much of the harmful solar radiation and helping to prevent the solar wind. from stripping away our atmosphere. The development of this magnetic field wasn't immediate or constant. Like a flickering candle flame, it waxed and waned, sometimes strong enough to provide excellent protection, other times weak enough that significant atmospheric loss could occur. During periods when the magnetic field was strong, Earth could hold on to more of its water vapor. During weaker periods, some of this precious resource would escape to space. It was a cosmic dance of gain and loss that would continue for hundreds of millions of years. Temperature regulation became another critical skill that Earth had to master. The planet needed to learn how to maintain temperatures that would allow water to exist in all three of its phases: solid, liquid, and gas. But with liquid water being stable over most of its surface, this required a delicate balance of atmospheric composition, volcanic activity, and solar radiation absorption. Volcanic activity played a surprisingly important role in this temperature regulation. While we often think of volcanoes as destructive forces, they were actually essential teachers in Earth's water retention lessons. Volcanic eruptions released not only lava and ash, but also enormous quantities of water vapor and other gases into the atmosphere. Some of this water vapor came from deep within the Earth's interior, where it had been trapped since the planet's formation. In essence, volcanic activity was helping to recycle and redistribute water between Earth's interior and its surface. The ash and aerosols released by volcanic eruptions also played a crucial role in temperature regulation. These particles could reflect sunlight back into space, causing temporary cooling periods that would allow more water vapor to condense and remain on the surface. Conversely, the greenhouse gases released by volcanic activity, particularly carbon dioxide, could trap heat and warm the atmosphere, preventing water from freezing solid across the entire planet. As millions of years passed, Earth slowly began to master these complex lessons. The cosmic bombardment gradually decreased in intensity, allowing the planet's surface to cool and stabilize. Volcanic activity continued but became more predictable and less catastrophic. The magnetic field strengthened and became more stable. And most importantly, the atmosphere began to develop a composition that could effectively retain water vapor while maintaining temperatures suitable for liquid water. During this period, Earth experienced what we might call its first major atmospheric evolution. The early atmosphere, composed primarily of hydrogen and helium left over from the planet's formation, was gradually replaced by a secondary atmosphere created through volcanic outgassing and modified by incoming cosmic material. This new atmosphere contained water vapor, carbon dioxide, nitrogen, and various other gases that would prove essential for water retention. The role of impact events during this period was complex and multifaceted. While large impacts could certainly vaporize surface water and blast it back into space, they also played important positive roles. Some impacts delivered not just water, but also gases that helped thicken the atmosphere and improve its heat retention properties. Others created large basins that would eventually become the first major bodies of liquid water on Earth's surface. One of the most remarkable aspects of this period was the development of what scientists call atmospheric hydrodynamic escape mechanisms. This is a fancy way of describing how planets can lose their atmospheres, but it's also the key to understanding how Earth learned to prevent such losses. Unlike smaller planets like Mars, which gradually lost much of its atmosphere to space, Earth developed several mechanisms to retain its atmospheric envelope and the water vapor within it. As Earth's surface gradually cooled and its atmosphere stabilized, Our planet was about to experience one of the most beautiful and transformative events in its entire history. The water that had been delivered by cosmic messengers and retained through careful atmospheric management was about to undergo its first great condensation, the process by which water vapor in the atmosphere would transform into liquid water. On the surface, this wasn't just a simple change of state. It was the birth of Earth's first oceans, and it happened in a way that was both gradual and spectacular. Imagine, if you will, standing on this ancient Earth as the first drops of rain began to fall. But this wasn't a gentle spring shower or even a thunderstorm as we know them today. This was precipitation on a scale that defies human experience. A rain that may have lasted for thousands, perhaps even millions of years. The sky would have been perpetually overcast, heavy with water vapor that had been accumulating in the atmosphere for eons, waiting for the right conditions to finally condense and fall to the surface. The process began subtly, as most profound changes do. As Earth's surface temperature dropped below the critical point where water vapor could no longer remain stable as a gas, tiny droplets began to form around microscopic particles in the atmosphere, dust from volcanic eruptions, crystalline fragments from meteor impacts, and various other nucleation sites that provided the foundation for water droplet formation. These first droplets were incredibly small, barely visible even if there had been eyes to see them. But they represented the first tentative steps in water's journey from the sky to the sea. The cooling of Earth's surface wasn't uniform or immediate. Different regions cooled at different rates, creating a patchwork of temperature zones across the planet. Areas that had been recently resurfaced by volcanic activity remained hot and dry, while regions that had been relatively stable for longer periods began to experience the first tentative condensation events. This uneven cooling created the planet's first weather patterns, primitive, atmospheric circulation systems that would carry water vapor from warmer regions to cooler ones, where it could condense and fall as precipitation. As the condensation process accelerated, Earth experienced weather phenomena unlike anything we see today. The atmosphere contained far more water vapor than our current atmosphere, and when it finally began to condense, it did so with tremendous intensity. Imagine storms that covered entire continents, with rainfall rates that would make the most severe monsoons seem like light drizzles. The sound of this ancient rain would have been thunderous, a constant drumming on the rocky surface that could be heard for hundreds of miles. But this wasn't just rain as we understand it. Much of the water falling from the sky was superheated steam that had been vaporized by the intense heat of impact events and volcanic activity. When this steam finally cooled enough to condense, it fell as scalding hot water that would hiss, and steam when it hit the still warm rock surfaces. In some areas, this hot water would immediately re-evaporate, creating vast clouds of steam that would rise back into the atmosphere only to condense and fall again in an endless cycle of atmospheric recycling. The chemical composition of this ancient rain was also quite different from modern precipitation. It contained dissolved gases and minerals from the atmosphere, giving it a chemistry that was both more complex and more corrosive than today's rainwater. When this chemically active water came into contact with the rock surfaces, it began the planet's first major weathering processes, chemical reactions that would gradually break down minerals and release new compounds into the water, beginning the complex chemistry that would eventually make life possible. As this great condensation continued, Earth's surface began to transform dramatically. The first puddles formed in low-lying areas, growing into ponds, then lakes, and eventually into vast bodies of water that would become the predecessors of our modern oceans. But these early bodies of water were nothing like the clear blue seas we know today. They were hot, mineral-rich, and constantly churning from the ongoing rainfall and atmospheric disturbances. The formation of these first substantial bodies of liquid water created a new dynamic in Earth's atmospheric system. Large bodies of water have tremendous thermal inertia. They heat up and cool down much more slowly than land surfaces. This meant that once Earth's first lakes and protoceans formed, they began to moderate the planet's temperature, reducing the extreme temperature swings that had characterized the earlier period. The presence of liquid water on the surface also increased the humidity of the atmosphere, creating more clouds and precipitation, which in turn delivered more water to the surface in a positive feedback loop. During this period, Earth also experienced its first major ice ages, not the relatively recent ice ages that covered parts of the continents with glaciers, but much more extensive freezing events that may have covered the entire planet with ice. These snowball Earth episodes occurred when various factors reduced solar energy, increased reflectivity from ice and clouds, or changes in atmospheric composition caused global temperatures to plummet below the freezing point of water. Across most or all of the planet's surface, these global freezing events might seem like setbacks in Earth's journey to become a water world. But they actually played important roles in the planet's water cycle evolution. When water froze into ice, it became temporarily locked away from the atmosphere, reducing humidity and changing weather patterns. But ice is also an excellent preservative. It protected water from being lost to space while allowing volcanic and geothermal activity to continue adding more water vapor to the atmosphere when these ice ages eventually ended, often due to increased volcanic activity or gradual changes in solar output. The stored ice would melt and add to the planet's growing water reserves. The chemistry of Earth's early water bodies was constantly evolving during this period. The water that fell as rain picked up various compounds from the atmosphere, acids from volcanic gases, minerals from impact debris, and organic compounds from cosmic sources. When this chemically active water pooled on the surface, it began to dissolve minerals from the rocks it contacted, gradually becoming more and more complex in its chemical composition. Iron was one of the most important elements involved in these early water chemistry changes. The young Earth's atmosphere contained very little oxygen, which meant that iron could exist in a dissolved form in water. This gave many of Earth's early water bodies a distinctive reddish or greenish color, quite different from the blue of modern oceans. As this iron-rich water was exposed to sunlight and various chemical processes, it began to precipitate out as iron-rich minerals, creating some of the oldest sedimentary rock formations we can still see today. The ongoing volcanic activity during this period also meant that Earth's early oceans were constantly being modified by underwater volcanic eruptions and the influx of hot mineral-rich water from geothermal sources. These underwater volcanic systems created the first hydrothermal vents, underwater geysers that spewed superheated, chemically rich water into the surrounding ocean. These vents would later prove to be crucial nurseries for the development of life. But even in these early days, they were important sources of chemical diversity in Earth's water bodies. As the Great Condensation period gradually came to an end, Earth had successfully transformed from a world with water vapor in its atmosphere to a world with vast oceans on its surface. But this transformation was far from complete. The planet had learned how to condense water from its atmosphere and retain it on its surface. but it still needed to learn how to maintain stable, long-term bodies of liquid water that could serve as the foundation for everything that would follow. The transition from atmospheric water to oceanic water represented a fundamental shift in Earth's character. Water in the atmosphere is transient. It can be easily lost to space or broken down by radiation. But water in large surface bodies is much more stable and protected. It can participate in complex chemical cycles, support intricate physical processes, and serve as a medium for the countless interactions that would eventually give rise to life itself. As our young Earth continued its cosmic dance through the early solar system, something truly remarkable began to happen. The violent outburst from countless volcanic eruptions wasn't just releasing random gases into space. It was crafting the very first threads of what would become our planet's protective atmospheric blanket. Picture, if you will, millions upon millions of volcanic vents across the scarred surface, each one breathing out a cocktail of water vapor, carbon dioxide, nitrogen, and other gases that would slowly, patiently begin to accumulate around our world. This wasn't the oxygen-rich atmosphere we know and love today. Oh no, this early atmosphere was something altogether different. A thick, heavy shroud dominated by water vapor and carbon dioxide, with traces of methane, ammonia, and hydrogen sulfide, creating a mixture that would have been utterly toxic to life as we know it. Yet this hostile brew was absolutely essential for what was to come. It was Earth's first attempt at creating the conditions necessary to hold onto liquid water. Even though the planet didn't quite know it yet, the beauty of this early atmospheric formation lies in its gradual, almost tentative nature. Earth wasn't rushing to create its atmosphere all at once. Instead, over hundreds of millions of years, these volcanic emissions slowly built up layer upon layer of gases, creating an increasingly thick blanket around the planet. Think of it like watching a spider weave its web in extreme slow motion, each strand of gas carefully added to the growing structure, creating something both delicate and incredibly strong. During this time, the sun itself was still finding its rhythm. Our young star was actually about 25 to 30% dimmer than it is today, a phenomenon scientists lovingly call the faint young sun paradox. You might think this would make Earth even colder, but here's where the story becomes truly fascinating. The thick atmosphere that Earth was so patiently building acted like a massive greenhouse, trapping heat in ways that would become crucial for the planet's water story. The water vapor in this early atmosphere played a particularly important role. Unlike the dry, thin atmospheres of some of our planetary neighbors, Earth's atmosphere was saturated with moisture from the very beginning. Every volcanic eruption contributed more water vapor, and every impact from a water-rich asteroid or comet added to this growing reservoir of atmospheric moisture. The planet was essentially learning to breathe water, each exhalation from its volcanic lungs adding to the humid, steamy atmosphere that surrounded it. As this atmospheric blanket grew thicker, something wonderful began to happen with temperature regulation. The carbon dioxide and water vapor acted as natural insulators, trapping heat from both the sun and the planet's own internal warmth. This greenhouse effect was far more intense than anything we experience today. Imagine the most humid, tropical climate you can think of. Then multiply that sensation across the entire planet. The surface temperature during this period likely averaged between 85 to 110 degrees Celsius, hot enough to keep water as vapor, but not so hot that it would be stripped away into space. The pressure of this early atmosphere was another crucial factor in Earth's water story. As more and more gases accumulated, the atmospheric pressure at the surface began to increase dramatically. Some scientists estimate that the pressure during this period could have been anywhere from 10 to 100 times greater than what we experience today. This intense pressure had a remarkable effect on water's behavior. It raised the boiling point significantly, meaning that water could remain liquid at much higher temperatures than it can today. Picture Earth during this time as a world wrapped in perpetual, thick fog. The sky would have been an endless canopy of dense, grey clouds, so thick that sunlight could barely penetrate to the surface. The entire planet existed in a kind of twilight, lit more by the red glow of volcanic activity, and the occasional flash of lightning than by direct sunlight. It was a world of mist and mystery, where the boundaries between sky and surface were blurred by the constant presence of water vapor. In this chapter of Earth's water story, we encounter one of the most important periods in our planet's history, a time when Earth became nature's most magnificent greenhouse. The thick atmosphere we described wasn't just a random collection of gases. It was a sophisticated heat-trapping system that would prove essential for liquid water's eventual triumph on our world's surface. The greenhouse effect during Earth's early years was nothing like the gentle warming we experience today. This was greenhouse warming on a scale that's almost difficult to imagine. The atmosphere, so rich in carbon dioxide and water vapor, created what scientists call a runaway greenhouse scenario, though thankfully not quite as extreme as what we see on Venus today. The heat from the sun, even though our star was dimmer, then would enter the atmosphere and become trapped by these greenhouse gases, bouncing back and forth between the surface and the atmospheric layers like light in a hall of mirrors. What made this greenhouse effect so special was its role in keeping water in its vapor form long enough for Earth to accumulate vast quantities of it. Without this intense warming, much of the water vapor being released from volcanoes and delivered by space rocks would have simply condensed immediately and then been lost to space through various processes. Instead, the greenhouse atmosphere created a kind of holding pattern, a warm embrace that kept water vapor suspended in the air while Earth figured out how to create the right conditions for liquid water to exist. The carbon dioxide in this early atmosphere deserves special mention. In our story, unlike today, when we worry about too much carbon dioxide, in Earth's early years, CO2 was absolutely essential for creating the warm conditions necessary for water's story to unfold. The volcanic outgassing was pumping enormous amounts of carbon dioxide into the atmosphere, perhaps 100 to 1,000 times more than we have today. This CO2 formed a thick, insulating blanket that trapped heat with incredible efficiency. But the water vapor itself was equally important as a greenhouse gas. In fact, water vapor is one of the most effective greenhouse gases in existence, and the early Earth's atmosphere was absolutely saturated with it. This created what climate scientists call a positive feedback loop. The warmer the atmosphere became, the more water vapor it could hold, and the more water vapor it held, the warmer it became. It was like Earth was learning to regulate its own temperature, finding the perfect balance to prepare for liquid water's grand entrance. During this greenhouse period, Earth's surface was a landscape unlike anything we can see today. Imagine vast, steaming plains where hot springs and geysers dotted the terrain. The boundary between liquid water and water vapor was constantly shifting. Puddles of hot water would form in low-lying areas, only to evaporate back into the thick atmosphere, then condense again as the temperature fluctuated. It was as if the planet was practicing learning through trial and error how to handle water in its various forms. The pressure during this time played a fascinating role in this water dance. At the surface, the atmospheric pressure was so intense that water could remain liquid at temperatures that would normally turn it to steam. In some protected valleys or depressions, pools of superheated liquid water might have persisted for thousands of years, creating Earth's first tentative attempts at permanent water bodies. These weren't oceans yet. They were more like nature's pressure cookers, where liquid water existed under conditions that seem almost alien to us today. Lightning was a constant companion during this greenhouse period. The thick, moisture-laden atmosphere was perfect for generating enormous electrical storms that would have made today's most impressive thunderstorms look like gentle spring showers. These lightning strikes played their own role in Earth's chemical evolution, breaking apart molecules in the atmosphere and creating new compounds that would eventually become important for life. The sky during this time would have been a constant light show of electrical activity, illuminating the misty world below with flashes of brilliant light. The greenhouse effect also created fascinating weather patterns that we can barely imagine. Today, with so much water vapor in the atmosphere and such intense heat, the planet experienced massive convection currents that moved moisture and heat around the globe in complex, swirling patterns. These weren't quite weather systems as we understand them today, but rather massive atmospheric rivers of hot, humid air that circulated around the planet, distributing heat and moisture in ways that helped maintain the delicate balance necessary for water's continued presence, and then, gradually, almost imperceptibly at first, something began to change in Earth's story. The great greenhouse that had dominated our planet for so long started to evolve, and with it, the conditions that would finally allow liquid water to make its permanent home on Earth's surface. This wasn't a sudden shift. Nature rarely works that way. Instead, it was a slow, gentle transition that took place over tens of millions of years, like the gradual changing of seasons, but on a planetary scale. Several factors contributed to this great cooling, each playing its part in the intricate dance that would finally allow oceans to form. First, Earth's internal heat source, that incredible molten core that had been driving so much volcanic activity, began to stabilize. The planet was no longer the chaotic, constantly reshaping world it had been in its earliest years. The rate of volcanic outgassing began to slow, which meant less water vapor and carbon dioxide being pumped into the atmosphere with each passing million years at the same time. A remarkable process was beginning to take place with the carbon dioxide that had been such an important part of Earth's greenhouse atmosphere. As the planet's surface began to cool slightly, some of the carbon dioxide started to dissolve into the hot pools of water that existed on the surface. This dissolved CO2 then reacted with rocks and minerals in a process called weathering, slowly removing carbon dioxide from the atmosphere and locking it away in solid form. It was as if Earth was learning to regulate its own thermostat, gradually turning down the greenhouse effect as conditions became more stable. The sun, too, was playing its part in this cosmic cooling story. As our star continued to mature, it was actually getting slightly brighter and more stable in its energy output. Paradoxically, this increase in solar energy helped with the cooling process by making the atmospheric circulation more efficient, helping to distribute heat more evenly around the planet and preventing the extreme hotspots that had characterized earlier periods. Perhaps most importantly, Earth's magnetic field was beginning to strengthen and stabilize during this period. This invisible shield, generated by the churning motion of molten iron in Earth's core, became increasingly effective at protecting the atmosphere from being stripped away by solar wind. Earlier in Earth's history, some of the water vapor in the atmosphere had been lost to space when energetic particles from the sun broke apart water molecules and allowed the lighter hydrogen atoms to escape. The strengthening magnetic field helped protect the precious water that remained. As the great cooling progressed, the first signs of what we might recognize as weather began to appear. The temperature difference between different parts of the planet started to create pressure gradients that drove wind patterns. These winds helped distribute heat more evenly, but they also began to create the first true water cycle. Water vapor would rise in warmer areas, travel through the atmosphere, and then condense in cooler regions. This was the beginning of the process that would eventually create Earth's first lasting precipitation. The cooling happened at different rates in different parts of the planet. The polar regions began to cool first, creating the first significant temperature gradients on Earth's surface. This temperature difference was crucial because it created the first stable patterns of atmospheric circulation. Hot, moisture air would rise near the equator, travel toward the poles, cool down, and then sink back toward the surface. This created the first primitive version of the atmospheric circulation patterns that still drive our weather today. During this gradual cooling period, something truly magical began to happen in the highest reaches of Earth's atmosphere. The thick blanket of water vapor that had characterized the greenhouse period began to thin out slightly. This allowed more heat to escape to space, which accelerated the cooling process. But it also meant that for the first time in Earth's history, the upper atmosphere became cool enough for water vapor to condense into tiny droplets, the first clouds in Earth's sky. These early clouds were unlike anything we see today. They were massive, dense formations that could span entire continents. The droplets in these clouds were larger and heavier than modern cloud droplets. Because of the high atmospheric pressure and the abundance of particles in the air that could serve as condensation nuclei. When these clouds finally became heavy enough to produce precipitation, it wasn't the gentle rain we're familiar with. It was more like a constant, heavy mist that fell continuously for thousands of years at a stretch. And so we come to one of the most pivotal moments in Earth's water story, the beginning of the first true rainfall in our planet's history. After hundreds of millions of years of existing primarily as vapor in the hot, thick atmosphere, water was finally ready to make its descent to Earth's surface in liquid form. This wasn't a single rainstorm or even a season of rain. This was a planetary transformation that would last for millions of years, as Earth learned to cry tears of joy at its own cooling. Picture, if you can, the very first raindrop to fall on Earth's surface and actually remain liquid. Somewhere, in some cooling valley or depression, as the atmospheric temperature finally dropped below the critical point where water vapor could condense and remain stable. That first precious drop made contact with rock that was finally cool, enough not to immediately turn it back to steam. It was a moment that no one was there to witness, yet it was perhaps the most important moment in the history of life on our planet. These first rains were nothing like the gentle showers we experience today. They fell from clouds that were incredibly dense and heavy, through an atmosphere that was still much thicker than our current one. The raindrops themselves were larger and fell with more force than modern rain because of the higher atmospheric pressure. When they struck the ground, they hit surfaces that were still quite hot, not hot enough to vaporize the water instantly. but hot enough to create enormous clouds of steam and to fill the air with the sound of sizzling and hissing as liquid water met heated rock. The early rainfall created Earth's first temporary lakes and rivers, though these early water bodies were fleeting things. They would form in low-lying areas during periods of heavy rain, persist for perhaps thousands of years, and then evaporate away as conditions changed. But each time this happened, a little more water remained, either soaking into the ground or pooling in deeper depressions. Earth was learning, through this process of trial and error, how to create permanent homes for liquid water. The chemical composition of these early rains was quite different from modern precipitation. The water carried with it dissolved gases. From the thick atmosphere, carbon dioxide that made it acidic, sulfur compounds that gave it a distinctive smell, and various other chemicals that had been floating in the atmospheric soup for millions of years. When this chemically rich rainwater struck the ground, it began a process of chemical weathering that would reshape Earth's surface and play a crucial role in regulating the planet's temperature. This chemical weathering was actually one of Earth's first great environmental feedback systems. The acidic rainwater would react with rocks and minerals on the surface, breaking them down and creating new chemical compounds. Some of these reactions consumed carbon dioxide from the atmosphere, gradually reducing the greenhouse effect and helping to cool the planet further. It was as if Earth was discovering how to use its water system as a planetary thermostat, automatically adjusting conditions to maintain the right temperature for liquid water to exist. The sound of these early rains must have been extraordinary. Imagine the constant patter of large raindrops falling on hot rock, the hiss and steam of water meeting heated surfaces, the rumble of the first rivers cutting channels through soft sediments, and the crash of the first waterfalls as water found its way from higher elevations to the growing pools and lakes below. For the first time in Earth's history, the planet had a voice that spoke in the language of flowing water. As the rainfall continued over thousands and thousands of years, the accumulated water began to collect in the lowest places on Earth's surface. These early basins weren't the smooth, defined ocean basins we know today. The planet's surface was still quite rough and irregular, scarred by impact craters and volcanic activity. But water, as it always does, found its way to the bottom of these depressions, creating the first substantial bodies of standing water on our planet. These protoceans were shallow and warm, more like vast hot springs than the deep, cool oceans. We know today the water was rich in dissolved minerals and chemicals, creating a kind of primordial soup that would later prove crucial for the development of life. The temperature of these early water bodies fluctuated dramatically with changes in atmospheric conditions, sometimes near boiling in the shallows, sometimes cooling to merely warm in deeper areas or during periods of heavy cloud cover. The formation of these first lasting bodies of liquid water created entirely new weather patterns on Earth. Water that evaporated from these warm pools and lakes would rise into the atmosphere, form clouds, and then fall as rain elsewhere on the planet. For the first time, Earth had a true water cycle: evaporation, cloud formation, precipitation, and collection that would continuously move water around the planet's surface. This water cycle helped to moderate temperatures and distribute heat more evenly, creating more stable conditions for liquid water to persist. As millions of years passed and the great rains continued their patient work, something truly remarkable began to emerge from Earth's gradual transformation. The scattered pools and lakes that had formed in various depressions around the planet started to grow larger and deeper. and some began to connect with one another through the ever-expanding network of rivers and streams. The planet was beginning to develop its first true ocean basins, and with them, the stage was being set for liquid water to finally establish its permanent reign on Earth. The formation of Earth's first ocean wasn't a single event, but rather a gradual accumulation that took place over tens of millions of years. Picture water as a patient artist, slowly but steadily painting across the canvas of Earth's surface. Each rainfall added another brushstroke, each river carved another channel, and each lake grew a little deeper and wider. The planet was learning to hold water not just temporarily, but permanently, creating the stable aquatic environments that would prove essential for everything that followed. These early oceans were unlike any body of water that exists on Earth. Today, they were much warmer, with surface temperatures often reaching 60 to 70 degrees Celsius, hot enough that you couldn't swim in them, but not so hot that they would boil away. The water was also much more chemically active than modern seawater. It contained higher concentrations of dissolved carbon dioxide, making it more acidic, and it carried a rich mixture of minerals and elements that had been leached from rocks. During the great weathering period that accompanied the first rains, the color of these early oceans would have been quite different from the blue we associate with water today. The high concentration of dissolved iron likely gave them a greenish or even reddish tint, while suspended particles from ongoing volcanic activity might have made them appear murky or cloudy. These weren't the crystal-clear tropical waters of a modern paradise. They were more like vast, warm, mineral-rich lakes that happened to cover much of the planet's surface. As these ocean basins filled, they began to play an increasingly important role in regulating Earth's climate. The enormous thermal mass of all this liquid water helped to moderate temperature swings, storing heat during warmer periods and releasing it during cooler times. This thermal buffering effect helped to create more stable conditions across the planet, making it easier for liquid water to persist in various locations and climates. The early oceans also began to drive more sophisticated atmospheric circulation patterns. The temperature difference between the warm ocean surfaces and the cooler land masses created pressure gradients that drove winds carrying moisture inland. These winds brought rain to areas that might otherwise have remained dry, helping to maintain the water cycle across a broader range of environments. Earth was developing its first truly global circulation system, powered by the interaction between its new oceans and its atmosphere. One of the most remarkable features of these early oceans was their role in carbon dioxide regulation. As we mentioned earlier, the oceans absorbed enormous amounts of CO2 from the atmosphere, gradually reducing the greenhouse effect that had dominated Earth's early climate. But the oceans didn't just store this carbon dioxide. They also facilitated chemical reactions that locked carbon away in mineral form on the ocean floor. This process, called carbon sequestration, helped to stabilize Earth's climate in the range where liquid water could exist comfortably. The depth of these early oceans varied dramatically from place to place. In some areas, they might have been quite shallow, perhaps only a few hundred meters deep, while in other locations, they could have reached depths of several kilometers. The variation in depth created different environments within the oceans themselves, with cooler, more stable conditions in the deeper areas and warmer, more dynamic conditions in the shallows. The tides in these early oceans were also quite different. From what we experience today, the moon was much closer to Earth then, which meant that tidal forces were much stronger. The difference between high and low tide could have been dramatic, perhaps tens of meters in some coastal areas. These extreme tides created vast intertidal zones where water would cover and uncover large areas of land on a regular basis, creating unique environments that cycled between aquatic and terrestrial conditions. As the oceans stabilized and matured, they began to develop their own internal circulation patterns. Temperature differences between surface and deep water, combined with the Coriolis effect from Earth's rotation, started to create the first ocean currents. These currents helped to distribute heat around the planet more efficiently, carrying warm water from equatorial regions toward the poles and bringing cooler water back toward the equator. This circulation system helped to create more moderate climates across a wider range of latitudes. The chemical evolution of these early oceans was also remarkable. As water interacted with rocks and minerals on the ocean floor, it gradually leaked out various elements and compounds, creating a complex chemical environment. Some of these chemicals would prove crucial for the development of life, while others helped to further stabilize the ocean's chemistry and temperature. The oceans were becoming not just repositories for liquid water, but sophisticated chemical systems that could support increasingly complex processes. Perhaps most importantly, these early oceans provided the stable, protected environment that liquid water needed to persist over geological timescales. Unlike the temporary pools and lakes of earlier periods, the oceans had enough thermal mass and chemical buffering capacity to resist rapid changes in temperature or acidity. They became Earth's first truly permanent homes for liquid water, marking the end of the transition period and the beginning of the stable, water-rich world that would eventually give rise to life as we know it, as Earth continued its slow dance. Around the young sun, something magical was beginning to happen in the cooling atmosphere above. The temperature had dropped just enough, like a pot of boiling water finally settling into a gentle simmer, for the water vapor that had been floating freely in the sky to begin its transformation. This was the moment our planet had been waiting for, though it didn't know it yet, the great condensation that would change everything. Picture, if you will, a summer morning when dew first appears on grass blades. The air, heavy with moisture from the night, finally reaches that perfect temperature where water can no longer remain invisible. It must become something you can touch, something real. This is what was happening to our entire planet, but on a scale so vast it's almost impossible to imagine. The atmosphere itself was becoming pregnant with possibility, ready to give birth to the first drops of liquid water Earth would ever know. The process began slowly, as all the most important things do. High in the atmosphere, where the air was thin and cold, tiny water molecules started to slow their frantic dance. They had been zipping around as vapor for so long, free and weightless. But now they were beginning to find each other. Like shy dancers at a cosmic ball, they started to pair up, then gather in small groups, then form larger and larger clusters. These clusters grew into droplets so small they could float on the gentlest breeze. But as more and more water vapor condensed, the droplets grew heavier. Gravity, that patient sculptor that had been shaping Earth since its very beginning, started to pull them downward. The first drops of rain in Earth's history were about to fall, and our planet held its breath in anticipation. But this wasn't going to be a gentle spring shower. The atmosphere was absolutely saturated with water vapor. Imagine every cloud you've ever seen packed into the sky at once, and then multiply that by 1,000. When the rain began, it was as if the heavens themselves had opened up. Water poured from the sky in torrents that would dwarf any hurricane you might imagine today. This was the deluge of all deluges, a rainfall that would continue not for hours or days, but for centuries. The raindrops fell onto a landscape that was still hot from Earth's violent youth. When they hit the superheated rocks, they turned instantly back into steam, rising up to join their sisters in the clouds above, only to condense again and fall once more. It was like a massive recycling system, with water constantly moving between sky and ground, steam and liquid, never quite finding a place to rest. But slowly, ever so slowly, the surface began to cool. The constant rain was like a patient nurse, gently cooling Earth's fevered brow with countless wet cloths. Each drop that fell carried away a tiny bit of heat, and gradually the temperature of the rocks began to drop. The water that fell no longer turned immediately to steam. Some of it stayed liquid for minutes, then hours, then days. This was the critical moment in Earth's story. The moment when liquid water first learned to survive on the surface. It was tentative at first, pooling in the smallest depressions. In the rock, tiny puddles that would evaporate quickly but were immediately replaced by new rain. These puddles were like Earth's first tentative words, simple sounds that would eventually grow into the complex language of oceans. As the cooling continued and the rain persisted, the puddles grew larger and lasted longer. They began to connect with each other, forming streams that trickled down the volcanic slopes. These streams carved the first channels in Earth's surface, creating pathways that would guide the water toward lower ground. Gravity was teaching the water where to go, showing it the way to its destiny. The water followed these rocky channels, gathering volume and momentum as it flowed. Small streams joined to become larger ones, and larger streams combined into the first rivers Earth had ever known. These rivers wound their way across the steaming landscape, carrying not just water but also dissolved minerals from the rocks. They flowed over. They were like Earth's circulatory system, carrying life-giving fluid to every corner of the planet. And where did these rivers go? They flowed downhill, always downhill, following the pull of gravity toward the lowest places. They could find these low areas, the basins and valleys carved by Earth's violent formation, became collection points for all this flowing water. Drop by drop, stream by stream, the water began to accumulate in these natural bowls. At first, these were just larger puddles, but as the rain continued its relentless fall, they grew deeper and wider. Days turned to weeks, weeks to months, months to years, and still the water kept coming. The puddles became ponds, the ponds became lakes, and the lakes grew so large they began to connect with each other. This was the birth of Earth's first seas, not the vast oceans we know today, but their humble beginnings. These early bodies of water were probably quite shallow and spread across many separate basins. They were like a collection of mirrors scattered across Earth's face, each one reflecting the stormy sky above and slowly merging with its neighbors. The water in these early seas was different from the pure H2O that had originally fallen from the sky. As it flowed over and through the rocks, it had picked up a whole catalogue of dissolved minerals. Salt, of course, but also iron, sulfur, phosphorus, and dozens of other elements that would prove crucial for the chemistry of life. The seas were becoming a rich soup of possibilities, a broth that would nurture the first stirrings of living things. But we're getting ahead of ourselves. The important thing to understand is that Earth had finally learned to hold on to liquid water after billions of years of existing as a hot, dry ball of rock. Our planet had developed the ability to maintain water in its liquid form on the surface. This was no small achievement. It required a delicate balance of temperature, pressure, and atmospheric composition that was almost miraculous in its precision. while Earth's surface was learning to cradle liquid water deep within the planet's core. Another crucial development was taking place far below the newly forming seas, in the heart of our world, where temperatures rivaled those of the sun's surface. Molten iron was beginning to move in a very special way. This movement would create something invisible but absolutely essential for Earth's water story, a magnetic field that would act like a protective shield around our entire planet. To understand why this magnetic field was so important, we need to think about what was happening in space around Earth. The sun, our life-giving star, was not just sending us light and warmth. It was also producing something much more dangerous, a constant stream of charged particles called the solar wind. These particles moved at incredible speeds, fast enough to strip away the atmosphere of any planet that couldn't protect itself. Imagine the solar wind as an invisible river of tiny bullets, all racing away from the sun at hundreds of miles per second. These particles carry an electrical charge, and when they encounter a planet's atmosphere, they can literally blast the air molecules away into space. This is what happened to Mars, without a strong magnetic field to protect it. The solar wind gradually stripped away most of its atmosphere, leaving behind the thin, cold air we see today. But Earth was developing something that Mars lacked, a powerful magnetic field generated by the motion of molten iron deep in its core. Picture the inside of our planet like a vast dynamo, a natural electrical generator powered by the heat left over from Earth's formation and the energy released by radioactive decay. The outer core, a layer of liquid iron and nickel about 1,400 miles thick, was constantly churning and flowing like a pot of metallic soup stirring itself. This flowing liquid metal created electrical currents, and these currents generated magnetic fields. It's the same principle that makes an electromagnet work, but on a planetary scale. The magnetic field lines stretched out from Earth's core, through the mantle and crust, and far into space, creating an invisible bubble around our planet called the magnetosphere. The magnetosphere became Earth's shield, deflecting most of the solar wind particles away from our planet. Instead of smashing into our atmosphere and blasting it away, the charged particles from the sun were guided around Earth, like water flowing around a rock in a stream. Some of these particles got trapped in Earth's magnetic field lines, creating the beautiful auroras, the northern and southern lights, that dance in our polar skies. This magnetic protection was absolutely crucial for keeping Earth's atmosphere intact, and the atmosphere was essential for maintaining liquid water on the surface. Without an atmosphere, water would simply boil away into space, regardless of temperature. The air pressure provided by our atmosphere is what allows water to exist as a liquid at the temperatures we find on Earth's surface. Think of it this way. If you've ever been to a high mountain, you know that water boils at a lower temperature than it does at sea level. This is because there's less atmospheric pressure pushing down on the water. Without any atmosphere at all, water would boil at any temperature above freezing. Earth's magnetic field helped ensure that our atmosphere stayed thick enough to keep our precious water in its liquid form. But the magnetic field did more than just protect the atmosphere from the solar wind. It also helped regulate the flow of charged particles from space that could affect the chemistry of the upper atmosphere. Some of these particles, when they interacted with atmospheric gases, could create chemical reactions that might have been harmful to the development of life. The magnetic field filtered out many of these potentially dangerous particles, creating a more stable environment for the complex chemistry that would eventually lead to living things. The strength and orientation of Earth's magnetic field have changed throughout our planet's history. Sometimes the field has been stronger, sometimes weaker, and occasionally it has even reversed completely, with magnetic north becoming magnetic south and vice versa. These changes have been recorded in the rocks, like pages in a vast book that tells the story of Earth's magnetic evolution. During the early period when Earth's first oceans were forming, the magnetic field was probably quite different from what we see today. It may have been weaker or more chaotic, still finding its rhythm as the core's convection patterns established themselves. But even this early, imperfect magnetic field was better than no protection at all, and it helped ensure that Earth's atmosphere remained thick enough to support liquid water. The development of Earth's magnetic field was like the planet learning to wear armor. This invisible protection allowed all the other processes we've been discussing, the cooling of the surface, the condensation of water vapor, the formation of the first seas, to proceed without the constant threat of atmospheric loss. It was one of several critical factors that made Earth the perfect place for liquid water to not just appear, but to persist for billions of years. As we think about Earth's magnetic field, it's worth marveling at the incredible precision required. For this protection to work, the field had to be strong enough to deflect the solar wind, but not so strong as to interfere with other important processes. It had to be stable enough to provide consistent protection, but flexible enough to respond to changes in the solar wind's intensity. Like so many aspects of Earth's story, the magnetic field represents a delicate balance that seems almost too perfect to be accidental. As Earth's first oceans spread across the cooling surface, our planet was achieving something remarkable, a state of balance that scientists now call the Goldilocks zone. Not too hot, not too cold, but just right for liquid water to exist. This balance was far more complex and delicate than simply being the right distance from the sun, though that certainly helped. It involved an intricate dance between atmosphere, oceans, and geology that would determine whether Earth could hold onto its water for the long term. Let's start with the atmosphere, which was still evolving as Earth settled into its new identity. As a water world, the early atmosphere was very different from the air we breathe today. It was thick with carbon dioxide, water vapor, and other gases that had been released from volcanic activity and the bombardment of comets and asteroids. There was very little oxygen that would come much later, thanks to life itself. This carbon dioxide-rich atmosphere created what we call a greenhouse effect, similar to what happens in a greenhouse where plants are grown. The CO2 acted like a blanket around Earth, trapping heat from the sun and keeping the surface warm enough for liquid water to exist. This was actually crucial during Earth's early history, because the sun was about 30% dimmer than it is today. Without this natural greenhouse effect, Earth would have been frozen solid, despite being in what we now consider the habitable zone. But here's where the story gets really interesting. As Earth's surface cooled and the oceans formed, something wonderful began to happen to all that carbon dioxide in the atmosphere. The CO2 started to dissolve into the seawater, just like the way carbon dioxide dissolves into a can of soda. This removed some of the greenhouse gas from the atmosphere, which allowed Earth to cool down a little bit more. As Earth cooled, more water vapor condensed into liquid, which meant there was less water vapor in the atmosphere. Water vapor is also a greenhouse gas, so removing it from the air allowed the planet to cool even further. But this cooling couldn't go too far, because if it did, the oceans would freeze, and then all the carbon dioxide that had dissolved in the water would be released back into the atmosphere, warming the planet again. This created a natural thermostat, a feedback system that helped keep Earth's temperature in the narrow range where liquid water could exist. If things got too hot, more CO2 would dissolve in the oceans, cooling the planet. If things got too cold, ice would form, releasing CO2 back into the atmosphere and warming things up again. It was like Earth had learned to regulate its own temperature, maintaining the perfect conditions for its precious water. But temperature wasn't the only thing that needed to be just right. The pressure at Earth's surface also had to be within a very specific range. Too little atmospheric pressure, and water would boil away into space. Too much pressure, and the atmosphere would become so thick and dense that the greenhouse effect would run away, turning Earth into a hellish world like Venus, where surface temperatures can melt lead. Earth managed to maintain just the right atmospheric pressure through another delicate balance. The planet was large enough to have strong gravity that could hold onto its atmosphere, but not so large that the atmosphere became crushingly dense. Earth's size was like baby bear's porridge in the Goldilocks story, not too big, not too small, but just right. The composition of the atmosphere was equally important. Besides carbon dioxide and water vapor, the early atmosphere contained nitrogen, which helped maintain pressure without contributing significantly to the greenhouse effect. There were also trace amounts of other gases, including some that would absorb harmful radiation from space, protecting the water on the surface from being broken apart by high-energy particles. Earth's distance from the Sun was, of course, another crucial factor in this Goldilocks balance. If Earth had formed closer to the Sun, like Venus did, the increased heat would have caused all the water to evaporate into the atmosphere, creating a runaway greenhouse effect. If Earth had formed farther out, like Mars, it would have been too cold for liquid water to exist on the surface for extended periods. But even being in the right orbital zone wasn't enough. Earth's orbit had to be stable over long periods of time. If the orbit were highly elliptical, bringing Earth much closer to the Sun at some times and much farther away at others, the temperature swings would be too extreme for liquid water to persist. Fortunately, Earth's orbit is nearly circular, providing consistent heating from the Sun throughout the year. Earth's rotation rate also played a role in maintaining the right conditions for liquid water. Our planet spins on its axis once every 24 hours, which creates a day-night cycle that helps distribute heat around the globe. If Earth rotated much more slowly, one side would become extremely hot while the other froze. If it rotated much faster, the weather patterns would be chaotic and extreme. The 24-hour day was another just right factor in Earth's water story. The tilt of Earth's axis, which gives us our seasons, also contributed to the stability of liquid water. The 23.5-degree tilt is large enough to create seasonal variations that help drive weather patterns and ocean currents, but not so large as to create extreme temperature swings that would freeze or boil away the oceans. This tilt has been stabilized by our large moon, whose gravitational influence helps keep Earth from wobbling too much as it spins. Speaking of the moon, this celestial companion played its own role in Earth's water story. The moon's gravitational pull creates tides in Earth's oceans, and these tides may have been important for mixing the early seas and helping to distribute heat and nutrients. The tidal forces also gradually slowed Earth's rotation from what was probably a much faster spin rate in the early days, helping to establish the stable day-night cycle we have today. All of these factors, atmospheric composition and pressure, distance from the Sun, orbital stability, rotation rate, axial tilt, and the presence of the moon, had to work together to create the conditions where liquid water could not just exist, but thrive on Earth's surface. Change any one of these factors significantly, and Earth might have ended up like Venus, with a thick atmosphere and crushing greenhouse effect, or like Mars, with a thin atmosphere and water that mostly exists as ice. The remarkable thing is how all these conditions came together at just the right time in Earth's history. It's as if the universe conspired to create the perfect environment for liquid water, setting the stage for all the amazing developments that would follow. This Goldilocks balance wasn't something that happened by accident. It was the result of countless interactions between Earth's various systems, each one fine-tuning the conditions to keep our planet's water in its liquid state. With Earth's oceans now established and the atmospheric conditions stabilized, something truly magnificent began to emerge. The planet's first great circulation systems, like the bloodstream of a living being, currents began to flow through the newly formed seas, carrying warmth, nutrients, and dissolved minerals from one part of the world to another. This circulation would prove to be one of the most important factors in maintaining Earth's ability to hold liquid water over the long term. The driving force behind these early ocean currents was the same energy source that had been shaping Earth's story from the beginning: heat from the sun. But now, instead of simply warming rocks and evaporating water, the sun's energy was creating temperature differences in the vast expanses of seawater that covered much of the planet's surface. These temperature differences became the engine that would drive ocean circulation for billions of years to come. Picture how this worked in those early seas. Near the equator, where the sun's rays struck Earth most directly, the surface water absorbed enormous amounts of heat. This warm water, being less dense than cold water, wanted to rise toward the surface and spread outward. Meanwhile, near the poles, where the sun's light arrived at a much shallower angle, the water remained cooler and denser, sinking toward the ocean floor. This created a massive conveyor belt of moving water. Warm surface currents flowed away from the equatorial regions toward the poles, carrying heat with them like a planetary heating system. As this warm water reached higher latitudes and began to cool, it became denser and started to sink. This cooler, denser water then flowed back toward the equator along the ocean floor, completing the circulation cycle. But Earth's rotation added another layer of complexity to this simple north-south circulation. As the planet spun on its axis, the moving water was deflected by what we now call the Coriolis effect. This meant that currents didn't flow straight north and south, but curved to the east and west as well, creating complex spiraling patterns that distributed heat and nutrients throughout the entire ocean system. These early ocean currents were incredibly important for Earth's water story, because they helped even out temperature differences across the planet. Without circulation, the equatorial regions would have become much hotter, while the polar areas would have been much colder. This extreme temperature variation could have led to all the water evaporating from the hot zones and freezing solid in the cold zones, making it much harder for liquid water to persist globally instead. The ocean currents acted like a massive air conditioning system, moving warm water toward the poles and cold water toward the equator. This helped maintain a more moderate temperature range across Earth's surface, keeping more of the planet within the narrow temperature band where water could remain liquid. It was another example of Earth's systems working together to maintain the delicate balance necessary for holding on to its precious water. The circulation wasn't limited to the oceans either. The atmosphere was developing its own circulation. Patterns, driven by the same temperature differences that powered the ocean currents. Warm, moist air rose from the equatorial regions, carrying water vapor high into the atmosphere. As this air moved toward the poles and cooled, the water vapor condensed and fell as rain. Then the cooler, denser air sank back toward the surface and flowed back toward the equator. This atmospheric circulation created Earth's first weather systems. Clouds formed where warm, humid air rose and cooled. Rain fell where the moisture-laden air could no longer hold all its water vapor. Winds blew as air moved from high-pressure areas to low-pressure areas, trying to even out the pressure differences created by the uneven heating of Earth's surface. The interaction between ocean and atmospheric circulation created an even more complex and effective system for distributing heat and moisture around the planet. Ocean currents influenced local weather patterns, while atmospheric winds drove surface ocean currents and affected the mixing of different layers of seawater. It was like watching two dancers learning to move together, each one responding to and influencing the other's movements. As these circulation systems developed and strengthened, they began to transport more than just heat and water. The moving seawater picked up dissolved minerals from underwater volcanic vents and carried them across ocean basins. Rivers flowing into the seas brought nutrients washed from the land, and the ocean currents distributed these life-giving chemicals throughout the marine environment. This mixing and circulation was creating something unprecedented in Earth's history, a global chemical reactor where different elements could combine in new ways. The ocean had become a vast laboratory where the building blocks of life were being stirred together in countless different combinations. Iron from hydrothermal vents mixed with phosphorus from eroding rocks, sulfur compounds from volcanic activity, combined with carbon from the atmosphere. Nitrogen dissolved in seawater encountered trace metals carried by ocean currents. The circulation also helped oxygenate the early oceans, though there was still very little oxygen in the atmosphere at this time. What little oxygen existed came from the breakdown of water molecules by ultraviolet radiation from the sun. The ocean currents carried this dissolved oxygen from the surface layers down into the depths, ensuring that even the deepest parts of the sea had at least some of this reactive gas. Perhaps most importantly, the great circulation systems helped stabilize Earth's climate over long periods of time. When one part of the planet experienced unusual warming or cooling, the currents would redistribute that heat, preventing extreme changes that might have disrupted the delicate balance necessary for liquid water. The oceans became Earth's thermal memory, storing heat during warm periods and releasing it during cooler times. This thermal buffering effect was crucial during the early Earth period, when the sun's output varied more than it does today, and when volcanic activity could inject large amounts of particles into the atmosphere, temporarily blocking sunlight and cooling the planet. The ocean circulation helped Earth weather these early climate disturbances, maintaining conditions suitable for liquid water throughout the ups and downs of the planet's tumultuous youth. As we think about these first great circulation systems, it's remarkable to realize that they established patterns that continue to this day. The basic principles of ocean and atmospheric circulation that developed during Earth's early water period still drive our planet's weather and climate systems. In a very real sense, Earth learned how to hold liquid water by learning how to move it around, creating a dynamic, ever-changing system that has kept our planet's water flowing for billions of years. As our Earth settled into its newfound stability, protected by its magnetic embrace and wrapped in an atmosphere that could finally hold its breath, something truly magical was about to happen. The planet had been carrying water vapor in its atmospheric blanket for so long, like a mother holding her child close to her chest, waiting for just the right moment to let it rest. Picture, if you will, the moment when the first raindrop fell on Earth. Not just any raindrop, but the very first one in our planet's entire history. It must have been such a tender moment, like the first tear of joy after a long, difficult journey. This single drop of water, born from the cooling vapors high above, began its gentle descent through an atmosphere that had never known rain before. The temperature had been dropping slowly, oh so slowly, like the way autumn gradually gives way to winter. But this wasn't a seasonal change. This was Earth learning to let go of its fever, learning to cool down after billions of years of burning heat. The sun, our faithful companion, continued to warm our planet just enough, but not too much. It was like finding that perfect spot. By a fireplace where you're warm but not uncomfortably hot, as the atmosphere cooled. The water vapor began to gather itself together, the way friends naturally come together at a party. These tiny molecules of water, which had been dancing wildly in the heat, started to slow their frantic dance. They began to hold hands with each other, forming the first clouds in Earth's sky. Imagine how different our planet must have looked. Then, with its very first clouds casting shadows on the rocky surface below, these early clouds were nothing like the fluffy, white cotton balls we see today. They were massive, heavy with the weight of all that water vapor, finally finding a way to come together. They stretched across the sky like great grey blankets, pregnant with the promise of Earth's first rainfall. The air itself seemed to shimmer with anticipation, thick with moisture that had nowhere to go but down. And then it happened. The first drops began to fall, hesitant at first, like a child taking their first steps. These weren't the gentle spring showers we know today, but rather a slow, steady beginning of something that would transform our planet forever. Each drop that fell was a pioneer, exploring a world that had never felt the kiss of liquid water on its surface. When these first raindrops touched the still warm rocks below, they didn't simply splash and disappear. Instead, they sizzled and steamed, turning back into vapor almost immediately. It was like watching someone trying to water a sun-baked garden in the middle of summer. The water wanted to stay, but the heat of the rocks wasn't quite ready to let it rest there yet. But Earth was patient, and the rain was persistent. Drop by drop, shower by shower, the surface began to cool. The rocks, which had been holding on to their heat like a warm blanket on a cold morning, slowly began to release their stored warmth into the cooling air. It was a gentle negotiation between the water and the stone, a quiet conversation about finding the right temperature for both to coexist peacefully. As this cooling continued, something beautiful began to happen. The raindrops started to linger, a little longer on the surface before evaporating. Instead of disappearing instantly in a puff of steam, they would rest for a moment, maybe two, before returning to the sky. It was like watching someone gradually learning to trust, taking small steps before making a bigger commitment. The landscape during this time must have been absolutely otherworldly. Imagine vast expanses of dark volcanic rock stretching as far as the eye could see, all under a heavy, grey sky that seemed to press down on the earth like a protective blanket. Steam would rise from every surface where the rain touched, creating an ethereal mist that made the world look soft and dreamlike. In the lower areas, where the land dipped down like natural bowls, the water began to collect in small puddles. These weren't permanent yet, mind you. They would appear with each rainfall and then slowly evaporate back into the atmosphere. But they represented something crucial. Earth's first experiments with holding liquid water on its surface. These temporary pools were like Earth's first attempts at keeping a diary, recording each rainfall and then releasing those memories back to the sky. But with each cycle of rain and evaporation, the surface cooled a little more, and the water stayed a little longer. It was a dance of patience, with both partners gradually learning each other's rhythms. The rain continued to fall, not in the violent storms we might imagine, but in a steady, gentle persistence that spoke of Earth's deep desire to finally hold onto its water. Day after day, year after year, century after century, this quiet rain fell on the cooling rocks. It was like a lullaby that never ended, a soft, constant reminder that change was coming. As the millennia passed, the puddles began to last longer. What had once evaporated in hours now lingered for days. What had once disappeared in days now remained for weeks. The rocks were learning to be cool and welcoming hosts to their liquid visitors, and the water was learning to trust that it could rest on the surface without immediately being sent back to the sky. During this time, the very first streams began to form. These weren't the bubbling brooks and rushing rivers we know today, but rather slow, tentative trickles of water that found their way from higher ground to lower ground, following the natural contours of the land like a child following a familiar path home. These early streams were pioneers in their own right, carving the very first channels in Earth's surface. They were gentle sculptors, working with infinite patience to create the first tiny valleys and grooves in the rock. Water, it turned out, was not just Earth's first liquid inhabitant, but also its first artist, beginning to shape and mold the landscape with its gentle, persistent touch. The sound of these first streams must have been the sweetest music Earth had ever heard. After billions of years of silence, broken only by the crack of cooling rock and the rumble of volcanic activity, here was something new, the gentle murmur of flowing water. It was like the planet's first song, a quiet melody that spoke of peace and possibility. As these streams grew bolder and more permanent, they began to connect with each other, forming the first primitive networks of flowing water. A trickle from one area would meet a trickle from another, and together they would become something larger, something more confident in their ability to stay liquid and keep flowing. The water was also beginning to encounter different types of rock and mineral formations, and each meeting was like a new friendship. Some rocks were welcoming and cool, allowing the water to rest easily on their surfaces. Others were still too warm or too rough, sending the water on its way to find more hospitable ground. Through these encounters, water began to learn the geography of its new home. This period of Earth's history, sometimes called the Great Cooling, was really a time of gentle negotiation between all the elements that would eventually make liquid water possible. The atmosphere was learning to hold just the right amount of moisture. The surface was learning to be cool enough to welcome liquid water. And the water itself was learning to trust that it could exist in liquid form without immediately being forced back into vapor. The very air during this time would have felt thick and humid, almost tropical in its moisture content, but without the warmth we associate with tropical climates today. It was a unique combination of coolness and humidity that created perfect conditions for water to transition from vapor to liquid and back again, over and over in an endless cycle of experimentation. And through all of this, the sun continued to provide just the right amount of energy to keep the process going. Not too much heat, which would have sent all the water back into vapor, and not too little, which would have frozen everything solid. It was a delicate balance, like a skilled chef adjusting the temperature of a delicate sauce, keeping it just right to achieve the perfect consistency as Earth's surface continued to cool and welcome its liquid water guests. Something remarkable began to emerge from all this gentle experimentation. The planet was inadvertently creating what would become one of its most beautiful and essential features, the water cycle. This wasn't something that happened overnight, of course. Like all the best things in nature, it developed slowly, organically, through countless small interactions between water, air, and earth. Think of it as Earth learning to breathe with water, just as our lungs take in air and release it in a rhythmic pattern. Our planet was discovering its own rhythm of taking up water from the surface and releasing it back down as rain. It was like watching someone learn to play a musical instrument, with each note getting clearer and more confident as time went on. The first hint of this emerging water cycle came when the temporary puddles and streams began to disappear on sunny days, sending their moisture back up into the atmosphere. But unlike the violent evaporation of the earlier hotter times, this was a gentle lifting, like the way morning mist rises from a lake. The water wasn't being driven away by intense heat. It was being invited upward by the natural warmth of the sun. High above, in the cooler reaches of the atmosphere, this evaporated water began to condense back into droplets, forming clouds that were more stable and long-lasting than the heavy, chaotic clouds of the earlier period. These new clouds had a different character altogether. They were lighter, more graceful, moving across the sky with a kind of purposeful elegance that suggested they knew exactly what they were doing. What was happening was that Earth was learning to juggle. Not literally, of course, but in the most beautiful metaphorical sense. Our planet was learning to keep water in constant, gentle motion between the surface, the air, and back to the surface again. It was a delicate balance that required perfect timing and just the right conditions. Much like a skilled performer keeping multiple balls in the air, the beauty of this emerging water cycle was in its simplicity and its complexity all at once. On one hand, it was beautifully simple. Water evaporates from the surface, forms clouds in the sky, and falls back down as rain. But the intricate dance of temperature, pressure, and timing that made this possible was incredibly complex, involving countless variables all working together in perfect harmony. As this cycle became more established, the landscape began to change. In subtle but important ways, the temporary streams became more permanent, carving deeper channels in the rock. The puddles in low-lying areas began to last longer, some of them becoming the first small ponds that could survive through multiple cycles of evaporation and rainfall. It was during this time that water began to truly explore Earth's surface. Like a curious child in a new playground, liquid water started to discover all the nooks and crannies of its new home. It flowed into cracks in the rocks, pooled in natural depressions, and began the slow, patient work of erosion that would eventually carve out valleys, canyons, and riverbeds. The relationship between water and rock during this period is particularly fascinating to consider. The rocks, which had been the undisputed masters of Earth's surface for so long, suddenly found themselves being gently but persistently modified by this new liquid neighbor. Water didn't fight with the rocks or try to dominate them. Instead, it worked with them, finding the easiest paths and gradually wearing away the rough edges. This erosion process was like a very slow, very gentle massage. Water would flow over the rocks, carrying away tiny particles of mineral and sediment, gradually smoothing and reshaping the surface. Over thousands and thousands of years, this gentle action began to create the first river valleys, the first smooth-bottomed lakes, and the first beaches where water met land in perfect harmony. The water cycle also began to sort and organize Earth's minerals in new ways. As water flowed over different types of rock, it would pick up various dissolved minerals and carry them to new locations. When the water evaporated, these minerals would be left behind, creating new concentrations of different substances in different places. It was like Earth's first recycling program, moving materials around the planet in a systematic and organized way. The atmosphere during this time was becoming increasingly sophisticated in its ability to handle water vapor. The early atmosphere had been somewhat chaotic, with water vapor mixed haphazardly throughout. But as the water cycle established itself, the atmosphere began to develop layers and patterns, with water vapor concentrating at certain altitudes and temperatures where it could most efficiently condense into clouds. These early clouds were becoming more predictable and organized as well, instead of the massive, unwieldy cloud formations of the earlier period. Earth's sky began to feature clouds that moved in patterns that formed and dissolved in regular cycles, and that could be counted on to release their water at appropriate times and places. The very first weather patterns were beginning to emerge during this period. Areas that received more sunlight would experience more evaporation, creating more clouds and, eventually, more rainfall. Areas that were naturally cooler or shadier would have different patterns of water collection and evaporation. Earth was beginning to develop its first regional climates, each with its own personality and characteristics. It's important to understand that this water cycle wasn't just a mechanical process of evaporation and condensation. It was becoming a living, breathing system that was constantly adjusting and fine-tuning itself based on changing conditions. When too much water accumulated in one area, the cycle would adjust to move some of that water elsewhere. When an area became too dry, the cycle would find ways to bring more moisture to that region. The timing of this water cycle was crucial to its success. If the cycle had been too fast, with water evaporating and condensing too quickly, it would have created chaotic weather patterns that couldn't sustain stable conditions. If the cycle had been too slow, with water sitting stagnant for too long, it would have created problems with mineral buildup and stagnation. But Earth found just the right pace, a rhythm that was neither too hurried nor too leisurely. As the water cycle became more established, it began to create feedback loops that helped stabilize the entire system. When the surface became too warm, more water would evaporate, creating more clouds that would shade the surface and cool it down. When the surface became too cool, less water would evaporate, reducing cloud cover and allowing more sunlight to warm the surface. It was like Earth's first thermostat, automatically adjusting conditions to maintain the perfect temperature for liquid water. The sound of Earth during this period would have been completely transformed from the earlier, quieter times. Now there was the constant gentle murmur of flowing streams, the soft patter of rain on rock, the whisper of wind moving through water vapor, and the quiet splash of water drops falling into pools and puddles. Earth had found its voice, and that voice was the sound of water in all its forms. The water cycle also began to create the first truly dynamic landscapes on Earth. Instead of static, unchanging rock formations, the planet now had features that grew and changed over time. Riverbeds that deepened and widened, lake shores that shifted with the seasons, and rock formations that were gradually sculpted by the patient action of flowing water. This dynamism extended to the atmosphere as well. The sky was no longer a simple dome of gases over the earth. It had become a three-dimensional space where water vapor moved in complex patterns, creating layers of humidity and dryness, areas of high and low pressure, and the beginnings of wind. Patterns that would carry moisture from one region to another. Perhaps most importantly, the establishment of the water cycle meant that Earth now had a reliable way to distribute water across its entire surface. No longer would water be confined to just the lowest areas or the places where it happened to rain most recently. The cycle ensured that water could reach every corner of the planet, creating opportunities for life and landscape development that had never existed before. The water cycle was also beginning to interact with Earth's other systems in increasingly complex ways. The movement of water was affecting the distribution of heat around the planet, helping to even out temperature differences between different regions. The erosion caused by flowing water was exposing new types of rock and mineral to the surface, creating new chemical interactions and possibilities. As we watch this water cycle establish itself, we're witnessing the birth of one of Earth's most fundamental and enduring systems. This same basic pattern of evaporation, condensation, and precipitation that was taking shape billions of years ago is still operating today. Still moving water around our planet, still maintaining the delicate balance that makes liquid water possible on Earth's surface. The water cycle was Earth's first great achievement in learning to hold liquid water. It wasn't enough to simply cool down enough for water to exist in liquid form. The planet also had to learn how to move that water around, how to keep it fresh and flowing, and how to maintain the right conditions for it to thrive. The development of the water cycle was like Earth, earning its master's degree in water management. With the water cycle now gracefully established and liquid, water finding its permanent home on Earth's surface, our planet was ready for its next great adventure. The vast expanses of water that had collected in the deepest basins and valleys were no longer just beautiful, shimmering mirrors reflecting the sky above. They were about to become nurseries for something completely unprecedented in our solar system's history. Life itself. Imagine, if you will, these early bodies of water as Earth's first meditation spaces. They were quiet, protected places where the most delicate and complex chemistry could begin to unfold without the harsh interruptions of violent weather or dramatic temperature changes. The water provided a gentle, stable environment where molecules could meet and interact with each other in ways that had never been possible in the chaos of the early Earth. The water in these early seas and lakes was quite different from the water we know today. It was rich with dissolved minerals and organic compounds that had been washed down from the rocks and carried by countless streams and rivers. Think of it as a very dilute soup containing all sorts of interesting ingredients that had been collected from across the planet's surface and mixed together in these water-filled basins. In the warmth of the early oceans, protected from the harsh radiation of space by Earth's atmosphere and magnetic field, something magical began to happen. The complex molecules that had been floating around in the water started to organize themselves in new and interesting ways. It was like watching a group of people at a dance, gradually finding partners and beginning to move together in harmony. The first spark of what we might call life was probably so small and subtle that it would have been impossible to notice if we had been there to observe it. It wasn't a dramatic moment with lightning and thunder, but rather a quiet, almost whispered beginning. Perhaps it was just a single molecule that learned to make copies of itself, or a small cluster of molecules that discovered they could work together to to accomplish, something neither could do alone. Water played the role of a perfect host for these early experiments in life. Unlike the solid surface of rocks or the chaotic movement of gases in the atmosphere, water provided a medium that was fluid enough to allow molecules to move around and find each other, but stable enough to let them form lasting relationships. It was like the world's first social club, bringing together compatible molecules and helping them discover what they could accomplish together. The chemistry of life required incredibly precise conditions, and water provided all of them. It was the perfect temperature, not so hot the molecules would break apart, and not so cold that they couldn't move and interact. It was the perfect density, thick enough to support complex structures, but thin enough to allow free movement. And it was the perfect chemical environment, neither too acidic nor too basic, but just right for the delicate chemical reactions that life depends on. As these first living molecules began to reproduce and spread through the water, they started to change the chemistry of the oceans themselves. Life wasn't just a passive inhabitant of the water. It was an active participant in shaping the very environment that supported it. The earliest living things began to process different chemicals, consuming some substances and producing others, gradually altering the composition of the water around them. This relationship between life and water was beautifully symbiotic from the very beginning. Water provided life with everything it needed to exist and thrive: a stable environment, dissolved nutrients, a medium for chemical reactions, and protection from harmful radiation. In return, life began to help water maintain the perfect conditions for its own existence, processing chemicals that might otherwise have made the water too acidic or too basic. The very first living things were incredibly simple by our standards, but they were revolutionary in their own time. They were basically just self-copying chemical reactions that had learned to sustain themselves using the resources available in the water around them. But this simplicity was also their genius. They were perfectly adapted to their aquatic environment, requiring nothing more than water and dissolved nutrients to survive and reproduce. As these early life forms multiplied and spread throughout the oceans, they began to diversify. Different populations adapted to different conditions within the water, some preferring slightly warmer areas, others thriving in cooler regions, some specializing in processing one type of chemical, others developing different chemical pathways. It was like watching a single song gradually develop into a symphony, with different instruments adding their own unique voices to the composition. The process of evolution was beginning, but it was happening entirely within the protective embrace of liquid water. Every adaptation, every new capability, every innovation in these early life forms was shaped by the properties and possibilities of their aquatic environment. Water wasn't just supporting life, it was actively guiding and directing the development of life through the opportunities and challenges it provided. One of the most remarkable things about this early period of life was how perfectly matched the living organisms were to their water environment. They had evolved to use water not just as a home, but as an integral part of their biology. Water was their transportation system, their food delivery mechanism, their waste disposal system, and their communication medium, all rolled into one. The early oceans during this time would have looked quite different from our modern seas. The water might have had a slightly different color, tinted by the minerals and organic compounds dissolved within it. There would have been no fish, no seaweed, no coral reefs, just vast expanses of water teeming with microscopic life forms, too small to see but busy transforming the chemistry of their world one molecule at a time. The relationship between these Early life forms and the water cycle was particularly fascinating. As water evaporated from the ocean surface and fell as rain on the land, it would pick up new minerals and nutrients from the rocks and soil, then carry these resources back to the oceans where life could use them. In this way, the water cycle became life's first global supply chain, constantly delivering fresh resources and removing waste products. Life in the early oceans also began to develop the first primitive forms of cooperation. Some organisms discovered that they could benefit by living close to others, sharing resources or helping each other process different types of chemicals. These early partnerships were the beginning of more complex relationships that would eventually lead to the development of multicellular life. The stability of liquid water was crucial to all of these developments. Life needed time to experiment, to make mistakes, to try new approaches, and gradually improve upon them. If the water had been constantly freezing and thawing, or evaporating and condensing, these delicate processes of evolution and adaptation would have been constantly interrupted. But the steady, reliable presence of liquid water provided the consistent environment that life needed to develop and flourish. As millions of years passed, the oceans became increasingly rich with life. What had started as a few simple chemical reactions had grown into diverse communities of microscopic organisms, each playing their own role in the complex chemistry of the sea. The water was no longer just a solvent containing dissolved minerals. It had become a living system, pulsing with biological activity. The waste products of these early life forms began to accumulate in the water, but rather than creating pollution, they often became resources for other organisms. One creature's waste product became another's food source, creating the first circular economies where nothing was truly discarded. Everything was recycled and reused. The oceans were becoming self-sustaining systems that could maintain themselves indefinitely. During this period, life also began to develop the first primitive forms of what we might call environmental engineering. Some organisms learned to modify their immediate surroundings to make them more suitable for survival. They might concentrate certain chemicals or create tiny structures that provided shelter, or develop ways to process toxins that might otherwise harm them. The temperature of the early oceans was perfectly suited to these biological innovations. It was warm enough to keep chemical reactions moving at a good pace, but not so hot as to break apart the delicate molecules that life depends on. This temperature stability was maintained by the interaction between the water, the atmosphere, and the energy from the sun. Another example of how all of Earth's systems were working together to support the emergence of life. The salinity of the early oceans also played an important role in life's development. The dissolved minerals in the water provided essential nutrients that life needed to build its cellular structures and power its chemical reactions. But the concentration of these minerals was just right, not so high as to be toxic, but not so low as to be insufficient for life's needs. As life continued to evolve and diversify in the oceans, it began to develop more sophisticated ways of interacting with water itself. Some organisms learned to control the movement of water through their bodies, using it for internal transportation and communication. Others developed ways to modify the chemistry of the water around them, creating favorable conditions for their own survival. The early oceans were becoming Earth's first laboratories, where life experimented with countless different approaches to survival and reproduction. Every successful innovation was preserved and passed on to future generations, gradually building up a library of biological solutions to the challenges of living in a water-based environment. Perhaps most remarkably, life in the early oceans began to develop systems for information, storage, and transmission. The first primitive genetic materials allowed organisms to record successful strategies and pass them on to their offspring, ensuring that beneficial adaptations wouldn't be lost. This was the beginning of biological memory, the ability of life to learn from experience and build upon previous successes. As life took its first tentative steps in Earth's ancient waters, the oceans themselves began to transform in ways that would have seemed impossible in the earlier sterile seas. What had once been simple collections of water and dissolved minerals were becoming complex, interconnected systems where countless forms of life worked together to create something far greater than the sum of their parts. The relationship between water and life during this period was like watching a perfect dance partnership develop. Water provided the stage, the music, and the space for movement, while life brought the creativity, the energy, and the purpose. Together, they began to create something beautiful and unprecedented, the world's first living oceans. These early living oceans were marvels of efficiency and cooperation. Every drop of water was alive with microscopic organisms, each one playing its part in vast networks of chemical exchange and mutual support. The water itself became a medium for communication, carrying chemical signals between different organisms and allowing them to coordinate their activities across vast distances. Think of it as Earth's first internet. But instead of electronic signals, it used chemical messages dissolved in water. An organism in one part of the ocean could release a chemical signal that would be carried by ocean currents to other parts of the sea, where different organisms would detect it and respond accordingly. This allowed for a kind of planetary scale, coordination that had never existed before. The chemistry of the oceans during this time was incredibly dynamic and complex. Life wasn't just living in the water, it was actively reshaping the water's chemical composition every moment of every day. Some organisms were consuming carbon dioxide and producing oxygen. Others were processing nitrogen compounds, and still others were concentrating and redistributing various minerals and nutrients. One of the most remarkable developments during this period was the emergence of photosynthesis, the process by which some organisms learned to capture energy directly from sunlight. This innovation transformed the oceans in profound ways, because it meant that life was no longer entirely dependent on the chemical energy stored in dissolved minerals. Instead, it could tap into the vast energy resources of the sun itself. The arrival of photosynthetic organisms was like the ocean's first energy revolution. These tiny creatures, floating near the surface where sunlight could reach them, began to convert solar energy into chemical energy that other organisms could use. They were essentially the ocean's first power plants, generating the energy that would fuel increasingly complex ecosystems. Water played a crucial role in photosynthesis, serving not just as the medium in which the process took place, but as one of the key ingredients. These early photosynthetic organisms learned to split water molecules using energy from sunlight, releasing oxygen as a byproduct. This was the beginning of the process that would eventually fill Earth's atmosphere with the oxygen that we breathe today. The oxygen produced by these early photosynthetic organisms initially dissolved into the ocean water around them, creating new chemical possibilities and challenges. Some organisms learned to use this oxygen for more efficient energy production, while others had to develop ways to protect themselves from oxygen's reactive properties. The oceans were becoming a testing ground for different approaches to dealing with this new chemical environment. As the concentration of oxygen in the oceans increased, it began to affect the water itself in interesting ways. Oxygen-rich water could support different types of chemical reactions than oxygen-poor water, creating diverse microenvironments within the same body of water. This chemical diversity provided new opportunities for life to specialize and adapt to specific conditions. The oceans during this period were also becoming increasingly structured and organized. Different depths of water had different temperatures, different pressures, different concentrations of dissolved nutrients, and different amounts of sunlight. Life began to adapt to these different zones, creating the first vertical ecosystems, where organisms at different depths specialized in different roles and functions. Near the surface, where sunlight was abundant, photosynthetic organisms thrived, converting solar energy into chemical energy and producing oxygen as a byproduct. In the middle depths, other organisms evolved to consume the organic matter that drifted down from the surface, recycling nutrients and energy back into the food web. At the bottom, in the darkest depths, specialized organisms developed ways to extract energy from chemical reactions that didn't require sunlight at all. The movement of water itself became an increasingly important part of these ocean ecosystems. Ocean currents, driven by differences in temperature and density, began to carry nutrients, oxygen, and even organisms themselves from one region to another. This circulation system helped to distribute resources throughout the oceans and prevented any area from becoming depleted or stagnant. The water cycle, which had been primarily a physical process of evaporation and precipitation, began to interact with biological processes in fascinating ways. When water evaporated from the ocean surface, it left behind not just dissolved minerals, but also organic compounds produced by living organisms. When this water vapor condensed and fell as rain, it carried with it chemical signatures of ocean life, connecting terrestrial and marine environments in subtle but important ways. Life in the oceans also began to develop more sophisticated ways of building structures and creating habitats. Some organisms learned to precipitate minerals from the water around them, creating the first biological structures like shells and skeletons. These innovations allowed life to build more complex forms and create three-dimensional habitats within the water column. The development of these structural capabilities was particularly important because it allowed life to modify its physical environment in addition to its chemical environment. Organisms could create shelters, build foundations for communities, and even modify water flow patterns around themselves. The boundary between living organisms and their environment was becoming increasingly blurred as communities of organisms became more complex and interconnected. They began to develop primitive forms of ecosystem regulation. When one type of organism became too abundant, it would deplete its food sources, creating opportunities for other organisms to flourish. This natural balancing act helped maintain stability and diversity within the ocean ecosystems. The oceans were also becoming increasingly efficient at recycling and reusing materials. When organisms died, their bodies would be broken down by other organisms, and their component materials would be returned to the water where they could be used again by new generations of life. Nothing was wasted. Everything was part of an endless cycle of renewal and regeneration. The temperature stability of the oceans was crucial to all of these developments. Water's high heat capacity meant that ocean temperatures changed slowly and gradually, providing a stable environment where complex ecosystems could develop without being disrupted by sudden temperature swings. This thermal stability was like a steady heartbeat that kept the entire system functioning smoothly. The chemical buffering capacity of seawater was equally important. The The dissolved minerals in ocean water helped to maintain stable pH levels, preventing the water from becoming too acidic or too basic as biological processes added various compounds to the marine environment. This chemical stability allowed life to develop increasingly sophisticated biochemical processes without having to constantly adapt to changing chemical conditions. During this period, the oceans also began to develop their first long-distance communication networks. Chemical signals produced by organisms in one part of the ocean could be carried by currents to distant regions, allowing for coordination and information sharing across vast distances. This was the beginning of planet-wide biological communication systems. The diversity of life in the oceans was expanding rapidly during this time, with new forms of organisms constantly evolving to take advantage of new opportunities and fill new ecological niches. Some specialized in consuming specific types of nutrients. Others developed unique methods of reproduction, and still others evolved novel ways of moving through the water or interacting with their environment. The oceans were becoming Earth's first global cities, bustling with activity and innovation. Every cubic meter of water contained thousands or millions of organisms, all interacting with each other and with their environment in complex webs of cooperation and competition. The water itself was the infrastructure that made this incredible complexity possible, providing the medium for transport, communication, and resource sharing. As we observe these ancient oceans teeming with life, we're witnessing the emergence of something truly revolutionary, the world's first biosphere. This wasn't just a collection of individual organisms living in the same environment. It was an integrated system where life and environment were so interconnected that they had become essentially one thing. The oceans weren't just containing life, they had become alive themselves. The success of life in the oceans was creating feedback loops that helped to maintain the very conditions that made life possible. Living organisms were actively regulating the chemistry of the water, the concentration of gases in the atmosphere, and even the temperature of the planet. Life had become an active participant in maintaining Earth's environmental stability. This period in Earth's history represents a fundamental transition from a planet that could support life to a planet that was actively shaped and maintained by life. The oceans had become the heart of a living planet, pumping nutrients and energy throughout the global system and maintaining the delicate balance of conditions that allowed life to flourish. As we reach the culmination of our journey through Earth's remarkable story of learning to hold liquid water, we find ourselves witnessing something truly extraordinary. A planet that hasn't just mastered the art of maintaining liquid water, but has woven water so deeply into its very identity that the two have become inseparable. Earth and water are no longer just companions. They are partners in the most beautiful dance in our solar system today. As you sit reading these words, that same ancient dance continues all around you. The water cycle that first emerged billions of years ago is still turning, still moving precious water from the oceans to the sky and back again. The same processes that allowed the first raindrops to fall on cooling rocks are still operating, still maintaining the delicate balance that keeps our planet habitable. But the dance has become so much more sophisticated since those early days. What began as simple evaporation and condensation has evolved into an intricate global system that regulates temperature, distributes nutrients, shapes landscapes, and supports the incredible diversity of life that makes our planet unique. Water has become Earth's circulatory system, its communication network, and its life support system, all rolled into one. The oceans today are the descendants of those first small puddles that formed when Earth finally cooled enough to hold liquid water. They carry within them the chemical memory of billions of years of evolution, the dissolved stories of countless generations of life that have called the seas their home. Every molecule of water in today's oceans has been part of this continuous story, cycling through clouds and rain, rivers and streams, plants and animals. For eons, the water in your own body is part of this ancient story too. The hydrogen and oxygen atoms that make up the water in your cells were forged in the hearts of stars and delivered to Earth by comets and asteroids billions of years ago. They've been part of oceans and rivers, clouds and raindrops, dinosaurs and trees, and countless other forms of life before becoming part of you. You are literally made of stardust and ancient water. Connected to the very beginning of our planet's water story, the relationship between water and life has become so intimate over the billions of years since life first emerged in the early oceans that it's impossible to imagine one without the other. Life has shaped the chemistry of water, and water has shaped the evolution of life in an endless feedback loop of mutual influence and adaptation. They have become co-creators of the world we know today, the forests and grasslands that cover our countenance today are essentially extensions of the ancient ocean ecosystems, adapted to live in partnership with water in its aerial and terrestrial forms. Trees reach deep into the ground to find water and lift it high into the air, where it evaporates from their leaves and rejoins the atmospheric part of the water cycle. They are living bridges between the earth and sky, helping to keep water moving through the global system. The weather patterns that bring us rain and snow, sunshine and storms, are all part of water's ongoing dance with Earth's atmosphere. Every cloud in the sky is a temporary gathering of water molecules that will soon continue their journey, perhaps falling as rain to nourish a forest, or snow to feed a river, or fog to water a desert. The atmosphere itself has become a vast ocean of water vapor, invisible but constantly present, ready to condense into liquid form. Whenever conditions are right, the rivers that flow across our continents are like Earth's bloodstream, carrying nutrients from the mountains to the seas, connecting distant ecosystems, and providing highways for life to spread and diversify. They are the descendants of those first tentative streams that formed when early rainwater found its way downhill. But they've become so much more than simple channels of flowing water. They are ecosystems in their own right, supporting everything, from microscopic bacteria to massive trees along their banks. The lakes and ponds, scattered across our planet, are like Earth's memories, each one preserving a unique record of the climate and life of its particular region. Some have existed for thousands of years, accumulating layers of sediment that tell stories of changing seasons, varying rainfall, and the evolution of the life forms that have called them home. They are living libraries of Earth's water history. Underground, hidden from our view, vast aquifers store ancient water that fell as rain thousands or even millions of years ago. This groundwater is like Earth's savings account, slowly moving through rock and soil, providing a steady supply of water to springs and wells, and serving as a buffer against drought and climate change. It's a reminder that water operates on timescales far longer than human lifespans, connecting us to the deep past and the distant future. The polar ice caps and glaciers are water's way of creating long-term storage and climate regulation. When too much water vapor accumulates in the atmosphere, some of it falls as snow and gradually builds up into ice that can persist for thousands of years. When global temperatures rise, this ice slowly melts and returns to the oceans, helping to moderate climate change. They are Earth's natural thermostats, using the phase changes of water to help maintain planetary stability. The incredible diversity of life on Earth today is a testament to water's success as a medium for biological innovation. From the deepest ocean trenches to the highest mountain peaks, from the driest deserts to the wettest rainforests, life has found ways to partner with water in every conceivable environment. Each adaptation, each new species, each biological innovation is another verse in the ongoing song of life and water. Human civilization itself is built around water, just as all life has always been. Our cities cluster around rivers and harbors. Our agriculture depends on rainfall and irrigation. Our bodies are mostly water, and our technologies increasingly recognize the central importance of water to everything we do. We are not separate from Earth's water story. We are one of its most recent chapters. But perhaps the most remarkable thing about Earth's relationship with water is how it continues to evolve and adapt. The water cycle is not a static system frozen in time. It's a living, breathing process that responds to changing conditions and continues to develop new capabilities. Climate change, caused by human activities, is creating new challenges for the water cycle. But it's also revealing the system's incredible resilience and adaptability. As global temperatures rise, the water cycle is intensifying with more evaporation from the oceans, more water vapor in the atmosphere, and more intense precipitation events. Some regions are becoming wetter, others drier, and the patterns of water distribution that life has adapted to over millions of years are shifting. But the fundamental processes remain the same, and life is once again adapting to new conditions, as it has so many times before in Earth's long history. The story of how Earth learned to hold liquid water is far from over. Every day, the dance continues, with water moving through its endless cycle of transformation and renewal. Every raindrop that falls, every river that flows, every cloud that forms is part of the same ancient story that began when our planet first cooled enough to welcome liquid water to its surface. And you are part of this story too. Every time you drink a glass of water, you're participating in the same process that has sustained life on Earth for billions of years. Every time you watch rain fall or snow melt, you're witnessing the continuation of the water cycle that first emerged in Earth's earliest days. Every breath you take contains water vapor that connects you to the global system that makes life possible. The water in your body will not stay with you forever. It will eventually return to the great cycle, perhaps becoming part of a cloud, or a river, or another living being. But the atoms themselves will continue their journey, carrying forward the story of Earth's long relationship with water. In this way, we are all temporary custodians of ancient water, brief participants in a story that is far larger and longer than any individual life. As we look to the future, the question is not whether Earth will continue to hold liquid water. The fundamental processes that make this possible are deeply embedded in our planet's structure and will continue for billions of years to come. The question is how we, as conscious participants in this story, will choose to relate to water and the living systems it supports. Will we recognize our role as partners in the ancient dance between Earth and water? Will we learn to work with the water cycle rather than against it? Will we understand that our own well-being is inseparable from the health of the global water system? The answers to these questions will determine not just our own future, but the future of countless other species who share this water world with us. The story of how Earth learned to hold liquid water is ultimately a story about patience, persistence, and the power of gradual change. It took billions of years for our planet to create the conditions that make liquid water possible, and it took billions more years for life to evolve in partnership with water to create the complex, beautiful world we inhabit today. In our fast-paced modern world, it's easy to forget that we are part of processes that operate on geological timescales, that the water we depend on is the result of planetary scale systems that have been developing for longer than we can easily imagine. But remembering this connection can give us a sense of perspective, humility, and wonder that enriches our daily experience of the world around us. Every time you see water in any of its forms, liquid, vapor, or ice, seeing the result of Earth's greatest achievement, learning to create and maintain the conditions for liquid water to exist on a planetary surface. This is not a common accomplishment in the universe. Most planets are either too hot or too cold, too large or too small, too close to their star or too far away. Earth found the narrow path between all these extremes and has been walking it successfully for billions of years, and so the dance continues, as it has since those first raindrops fell on the cooling rocks of the early Earth. Water rises from the oceans to the sky, gathers in clouds, falls as rain and snow, flows in rivers and streams, soaks into the ground, nourishes countless forms of life, and returns to the sea to begin the cycle again. It's a dance of such beauty, complexity, and reliability that it has become the foundation for everything we know and love about our planet. In this dance, we find not just the story of how Earth learned to hold liquid water, but the story of how water learned to hold Earth together, creating the conditions for life, shaping the landscape, moderating the climate, and connecting every part of our planet in an intricate web of flowing, cycling, life-giving water. It's a partnership that has created wonders beyond imagination and continues to create new wonders every day. Thank you for staying with me through this peaceful journey into how Earth learned to hold liquid water. It's been such a joy to explore with you the incredible story of our planet's relationship with this most precious substance. From those first tentative raindrops on cooling rock to the vast, life-filled oceans of today, we've witnessed a tale of patience, persistence, and the most beautiful partnership in our solar system. I hope this gentle exploration has helped you see water in a new light, not just as something we use in our daily lives, but as the result of billions of years of planetary evolution, as the foundation of all life on Earth, and as our connection to the ancient story of our world. The next time you see rain falling or waves lapping at the shore, you'll remember that you're witnessing the continuation of a dance that began when our planet was young and will continue long after we're gone. Water is all around us, within us, and part of us in ways that connect us to every other living thing on Earth and to the planet itself. We are all children of the same ancient oceans, all participants in the same eternal water cycle, all part of the same beautiful story of how Earth learned to hold liquid water and, in doing so, learned to hold life itself. If you enjoyed this peaceful journey through deep time and found comfort in Earth's gentle story of water, I'd be so grateful if you'd consider subscribing to join our little community of curious souls. There are so many more wonders waiting to be explored together. So many more stories of our amazing planet and universe that we can discover in this same gentle, thoughtful way. Take care of yourself, stay curious, and remember that every drop of water you encounter is part of this magnificent, ongoing story. Until we meet again in another peaceful exploration, May you find wonder in the world around you and comfort in knowing that you are part of something far greater and more beautiful than we can fully comprehend.